Thailand. He is also director of the Center of Excellence in Glass and Material Science, Thailand. He published more than 500 papers and his impact factor more than 800. His citation is more than 5,000. His H index 36, I-10 index 119. He is one of the scientists whose work on a single crystal luminescence glass material. Now I would like to invite Dr. Jakrafang to deliver his talk. Uh, okay, sir. Dr. Jakrapang, please share your screen and unmute your mic. Please, sir.
Hello, hello, Dr.
Yes,
Falak.
sir.
How are
Yes, sir.
you? Hello,
I'm
Pakistan
fine, sir.
friends.
I'm fine,
Yeah.
sir. How are
Okay.
you, sir?
Let me open. Let me open my camera. Okay.
Uh,
So
okay.
I'm fine.
Nice
Hope
to see you,
everyone
sir.
be. Yeah, nice to see you. Yeah.
Okay, sir.
So let me share my screen.
Yes,
Wait a
sir.
minute, please.
Okay, sir.
So can you see my screen?
Yes, sir.
Okay. So this is my screen. Okay.
Yes, we can
So
see, sir.
before I'm talking, yeah. So very thanks for Dr. Rani, chairman, right?
Yes, sir.
That he emailed to me for invite me for to be a speaker today. And thank you, Dr. Falak, to invite me also. And we have the many collaboration work together. Okay, not only Dr. Falak, we also have the many collaboration with Pakistan researcher. Let me show you later in my slide. Can we start now? Can I start now?
Yes, sir. You can start now, please, sir.
Okay, so I will use around 40 minutes for my talk. So today, this my talk is Titan is X-ray and proton and photoluminescent behaviors of samarium T plus dope high density tungsten gadolinium borate scintillating glass. So this is a collaboration work between Thai and Korea and just Thai and Korea work together. So this is my topics today. Topic is I will give a time for introduction about glass lab at Nakhon Pathom Ratchapat University in my group, and then concept of glass materials and lanthanide plus ion, luminescent mechanism of glass doped with lanthanide plus, and example of luminescent of lanthanide plus in glass. In today we are focused on samarium T plus and conclusion. So this is my country. The left picture is Thailand. As you can see, my province is in the central of Thailand, just west from Bangkok. Bangkok is capital city, around 1 hour by car, and around just 1.5 hour from international airport in Bangkok. So if we take a flight, just 5 hours to Islamabad. So this is a collaboration. So we have many collaboration in our group, like Korea, Japan, Vietnam, Myanmar, Indonesia, Pakistan, Russia, India, and Turkey. So also in Pakistan, we have the close cooperation work with Professor Guro in Aquam and Dr. Falak in the University of Brunei. This is our group. We have 13 members in our groups, and we work many class system. Yeah, you can see our motto is all classes we can. So some people work on the silicate glass in the left side. Some people work on the luminescent research group like the borate, phosphate, oxyfluoride, and telluride. Some people work on the radiation physics laboratories. So we have 13 faculty members in our groups. So now we have the one visiting researcher from India, Dr. Raja, and one postdoc and one researcher here, 10 students, let's say 12 PhD students and 7 master. So because of the virus situation, this is a little bit difficult for international student now, but I hope it will be better soon, very soon. So we are always accept student from our collaboration, like from Indonesia, from Pakistan, from India, and until now we have let's see, 1, 2, 3, 4, 5. Dr. Falak, Dr. Lubna, Dr. Muhammad Choi, Dr. Khan work with our group. Or the last people is Dr. Irfan. Yeah. Now 5 people visit our groups in Nakhon Pathom in Thailand and publish many works together. So many works together from each people. Not only people from the Pakistan, some from Indonesia also. So this is an instrument in our lab. So we have many glass furnace, big, medium size and big scale size. We also have the XRD and FTI and XRF instrument, gamma ray spectrometer with many scintillation crystal. You can see in the slide, and optical instrument like the ABI refractometers, UV visible, NIR, photoluminescent, X-ray induced luminescent, and some software for calculation. We also have the physical and mechanical study instrument like the densitometer, ultrasonic fluorometer to measure the speed and, let's say, velocity of the ultrasonic wave and amplitude. Then you can calculate the mechanical property of the materials. We also have the micro Wicker hardness and mole hardness scale tester. So this is in the last 5 years. If you search from the bibliometrics analysis in glass and Scopus, we also work many work in glass and luminescent keyword. Not only that, if you investigate like the material science keyword in the Scopus, so you can see the most publication within our group now. So from that achievement, we published, as Dr. Falak introduced, so we published 95 only Q1 and Q2 paper in ISI, in high impact factor journal. So this is not because of me, because of our collaboration. We have very strong publication together. And we have published, this is Scopus database and just data. We also have IM also have the top 2% of the world scientists from the report in the last year. So let's skip to the glass preparation. So how we can prepare the glass? The glass can prepare by technique we call melt quenching technique. So how you melt the glass until above their melting point? Let's say glass is not crystalline materials. Glass is amorphous material. So glass is not exact melting point. So that means there will a little bit change viscosity with temperature and then completely melt. After that, you take it out immediately from furnace. You can see from this. Now this process, you take it out immediately when very hot, and pouring to the mold. You can call this process is the melt quenching technique. Melt quenching technique. That's it. This is you can see this is a 1 kilo. This is a 10 kilogram furnace. In this furnace, its temperature is around 1200. Okay, you can see this the left video. You can see more easier. Okay, so that is a picture for glass melting process. This is a very conventional glass melting process. We call we call melt quenching technique. So actually, glass is a material in your everyday life. Glass is a material in your everyday life. So, but actually, so glass is also designed for many material for advanced application, especially on the emission base, like the laser materials, solid state lighting material, optical fibers, scintillation materials, especially in the scintillation material. The after we have very check the more scintillation material need in market now, and the market value is maybe 900 million US dollar in next 2 or 3 years from now. So how you can use the scintillation materials? So in the high energy and nuclear physics, in the radiation monitoring, X-ray imaging, in the medical application, neutron imaging, archaeologies, meteorologies, and homeland security. Many applications. So what is the definition of glass? Actually, so let me back to the last slide. Actually, the all scintillation material now in commercial market, most of them are the single crystal material. Just for example, sodium iodide crystal, cesium iodide crystal, bismuth germanate crystal. How we can develop the cheaper and usable in another technique. And so, sorry, for another material. This research is focused on glass materials. So you can see this is a definition of glass. The glass is an inorganic product of fusion which has cooled to a rigid condition without crystallizing. The key point is the without crystallizing. We call amorphous materials. So you can see from this chart, if you melt until from the left to the right, you can see after you melt any material to the completely melt, then when you cool down, if you cool down and you take time, you can get crystal. That means you have a time to rearrange atomic rearrangings. Then crystalline will be happen. Sometimes crystalline phase and amorphous phase is mixed together. But if you have cool down very fast, the technique called melt quenching technique, cool down very fast, you can call the fast, you can get the glass materials. So when you look into the atomic arrangement, you can see glass that is amorphous material is randomized structure. That means atom is not a pattern, but in crystalline atom there is pattern in atom. So in case of any chemical, we can divide simply divide to the three parts of the chemical in glass. The first is a glass former. For example, silicon dioxide, boron oxide, phosphorus oxide, thulium oxide, and germanium oxide. Second one is a modifier. Modifier is a break bond of the glass former, reduce melting point and reduce viscosity. The good example of the modifier, for example, is alkali oxide, like the sodium carbonate or sodium oxide in glass matrix, lithium carbonate. Any alkali is act as a glass modifier, but need the appropriate concentration also. And the last one is intermediate. Intermediate is not glass former, but can bond between glass former together and make glass is a more uniform. For example, aluminum oxide is a good for intermediate, but in case of the modifier and intermediate, please remind that it depends on type of glass formula and your concentration and also preparing condition. So that means sometimes the same oxide, sometimes they act as a modifier, but sometimes they act as a intermediate, depend on your preparing conditions. So let's keep to the luminescent property of the lanthanide. Why we choose lanthanide for the emission band? The lanthanide is a good because of intense emission and stable in different hosts, and also that intense emission is also sharp emission. Sharp emission like the, for example, samarium is emission is a main emission is 600 and so on that I show in this slide. So you can see from the lanthanide. So the good emission property is come from the F block electron that chill by outside electron. That means not much disturbing by any ligand when they have an emissions. It's different from transition ion. When you change ligand that means you change host from the one class formula to the second class formula to the another class formula. Maybe your emission is different from glass to the polymer or to the plastic to the solution. Maybe your emission is a little bit not little bit change, maybe big change also possible. But from the lanthanide is not much big change because of is not much disturbed by ligand to their emission. So this is a absorption spectra, and you can see the sharp spectrum of the lanthanide. In this case is NdT plus, niobium T plus, compared with the transition. In this case, red line is a chromium T plus ion. So in this work, we also design X-ray and neutron detection, deciding glass composition. But we work for X-ray first, and we design glass formula using the tungsten oxide because tungsten is a high density. Tungsten is the highest density element in the periodic tables. Also, good transparent by Borate glass structure and good interaction with X-ray and neutron. X-ray is a tungsten. Gadolinium is also high Newton cross-section. Boron is also high Newton cross-section. Good energy transfer from host to luminescent center and strong emission using Nd in this formula. And this is strong emission from SM. So this is design of the glass formula in this work. And then we mix together with this composition. This paper is already published in the somewhere else. I'm not sure, maybe Journal of Alloy Compound last year from our groups. So you can see that we wetting the chemical by this composition, melt, pouring, and then you get the glass after cut and polishing. So you can see that melt quenching technique. You can see that is more than 1200 degrees Celsius in this. Okay, so what is the instrument we use in this work? This is for density measurement. We use just simple microbalance using the Archimedes principle, absorption spectrometers, temperature dependence, luminescence. This measurement has been done in the Korea, in Kangpuk National University. XRD, photoluminescence, X-ray induced luminescence, and pulse X-ray decay curve. We also measure decay time using X-ray excitation. So this is also has been done in Korea also with Professor Hong Chu Kim group. So this is result. You can see that the hourglass is show pattern that no sharp peak. That is confirmed that this is amorphous nature of this glass system. And then this is smaller volume is when changing of the SM, samarium concentration, molar volume is decreased, but density is higher. I mean, keep going up until 6.18. So how big it is? From the literature, we are the biggest density now. I mean, this is the highest density in the literature now for the glass materials from our group. So This is just for comparative study. So what is the good thing of the highest density? The high density is mean high interaction of the X-ray and radiation. I mean the high energy photon. So let's see the absorption spectra. You can see in the absorption spectra, this also higher with higher samarium concentration. So and the highest band in shortest wavelength is 403 in the visible regions here. The state of the transition is shown in the picture. Actually, the state of the transition of each peak is the same. I mean, when you did it, let me talk for the student who work on this. You from the first time, maybe it's difficult for you, but if you have more take time for them, it will be more easy because pattern is also the same for submarine, but concentration, but intensity, the ratio of each peak may be different. You have to pay more attention to identify what is the peak transition come from. So this one is a 403 nanometers is the highest one, and you can also find many peaks, but all peak is also correspond with the samarium T plus ion in glass. This also confirm that the samarium is show 3 plus ion in glass also in this work. Let's see the excitation spectra. From the excitation spectra, we also design one more experiment. We also have a glass with samarium for 0.0, that means no samarium. And then with 0.1, 0.5, 1, and 2 samarium. And then we also have the pink line, that means without tungsten. Why we need that? We have to prove that what is the Bord peak come from. When you don't have this tungsten, Bord peak is disappear. You can see from the pink line. That means this Bord peak is come from tungsten oxygen charge transfer band. So this is also a good investigation from tungsten. And then when you have the GD, you can see more easily see the GD absorption, excitation from 275, 3 and 11, and then another peak is come from samarium from this excitation for emission fixing at 600 nanometers. This means when you want to observe 600 nanometer emission, you can excite under this peak also. But the best one from samarium should be come from 403. The best one from gadolinium should be come from 275. That's be confirmed by without tungsten glass network in this work. Also, this is excitation. So as you can see, this is a Bord peak. Under this Bord peak is auto tungsten charge transfer. You can excite in any regions, but the highest one is around 311 also. So this is like the overlap between tungsten and gadolinium. Anyway, for the emission observation, you can see that 275 excitation by gadolinium. The highest peak from samarium emission is 600. It's also the same with tungsten charge transfer excitation. 600 emission is coming out, and then for 300 and 403 nanometer samarium excitation, this is excite directly to the samarium band. You can find the 600 nanometers. So this result is also published in the Journal of Alloy and Compound last year. This is one of our good results. You can see this emission from the GD is lower and lower and lower from the zero samarium. What happened? That means this emission from gadolinium is not occur after no more samarium. It means the gadolinium is transfer the energy to the samarium ion in this glass structure formula. So you can see that the concentration quenching is around is a 1% mole for each excitation, and this is a diagram for the excitation. You can see the blue line is excited by GD emission. The 311 actually is GD. I draw GD, but actually is also a charge transfer between GD and tungsten also. Charge transfer between tungsten and oxygen overlap with GD 3 plus level also. And then this is emission that keep decreasing when higher concentration of samarium oxide, and then energy is transferred to samarium side, then emission is happen. So for the decay time, this decay time is used simple photoluminescent instrument using the xenon lamp excitation, and decay time is around millisecond region and keep decreasing with increasing of samarium concentration, and you can determine the Q value is higher. That means probability of the cross relaxation between samarium ion is increased with increasing of the samarium concentration in glass. From this technique, when your decay time is not single exponential behavior, you have to do a technique we call the IH model to fit decay time, and you get new values. So this is a temperature dependent luminescence. As I told you, we set up the temperature dependent lowest to the 10 Kelvin from the room temperature. Let's say 300 Kelvin, 200, 110. So what happened? Because of the vibration in the structure in the host is lower by decreasing temperature, so emission is coming out because the losing in the photon behavior is reduced. How much time from the 300 Kelvin down to 10 Kelvin, the light is come out more around 3.7 times. That means you can use better at the lower temperature and sometimes in the cryogenic application. So this is a very easy, simple video just for seeing what is the color that emits from the hourglass. You can see the very beautiful yellow color under UV lamp and laser excitation, just different excitation. So this is the X-ray induced luminescence spectrometer, and you can find that one behavior is very interesting by excite with X-ray. Actually, from the photoluminescence, thickness is always higher, but in the X-ray excitation, X-ray is higher. 650. Let's say 647 is higher emission. That is interesting behaviors. So this is because of different interaction between photoluminescence and X-ray luminescence. Photoluminescence, we excite directly to the luminescent band, but in case of X-ray, we excite cross the band. I mean, this is the interband excitation. So because the high energy X-ray is interband excitation, then scintillation property will be happen. After that, there will be like the thermalization, then electron is transferred to the luminescent band later. Then finally, luminescence is coming from the same SM doping. But interesting result is this peak is higher than 600 nanometers, and decay time is around similar value with photoluminescent decay time is around 0.2 millisecond. So let's see. This is decay time from PL is around 1.2 and then decrease to 0.4. So, but why the X-ray luminescent decay time is lower, a little bit lower, but in the same range, it is a millisecond region. Because of decay time, in these measurements, all peak is coming out in the same time. But in case of the photoluminescent, we observe just only one peak decay time. Let's say many people observe on the highest peak 600 nanometer, but in this case we observe all peak together. Like this decay time is average decay time of all light that coming out to the oscilloscope that we use in these measurements using X-ray plus X-ray excitation. And also this is also measured in Korea. In Kangpuk National University, we also measure that one irradiated by proton irradiation and see what happened in the luminescence. The same, this peak is also higher than this peak, is different from the photoluminescent one. Very interesting. So this is my conclusion. The glass in this work are very heavy and density is up to 6.18. Absorption is show the samarium T plus ion in glass, and photoluminescence is show highest at 600, but in for the radiation, X-ray and proton. X-ray and proton is also respond, high interaction with density of the materials. So that is show same behaviors, is around 650. Quenching concentration is a 1% mole, and temperature dependent is higher, around 3.7 times, and decay time is in the millisecond region. Let's say 1 down to 0.2 millisecond, and color of emission is when you observe by eye is orange. And many applications in future, maybe for the X-ray detection, inspection system, medical diagnosis, industry effect inspection, and security checking. But we have to design the electronic system to convert that light to the picture. That is our future work. So this is my acknowledgement, the Royal Golden Jubilee Program and National Research Council of Thailand. Thank you very much. That's all for my talk today.
Thank you very much, sir.
Yeah.
Thank you very much, sir, for such a nice talk. And if someone have a question, please unmute your mic and ask the question.
Yes, please.
Hello. Can I ask one question?
Yes, please.
Yeah, Professor Kyung Pok, thank you very much. This is Han from Japan, Riken. So, very nice talk. Yeah, congratulations. I'll just ask one question about you showing some spectra of around 275 nanometer. From your
which spectrum? Excitation or emission?
Yes, emission spectra.
Emission. Okay, let me show the slide. Please keep talking. Thank you.
So, can you control only single spectra around 275 nanometer by, in your crystal of the glass, or you maybe cadmium? This, I believe you say it's from GD3, which was this emission originated from the GD3. Yes, something like that. Yeah, here we can see this. So it's a almost ultraviolet region, UV.
Yeah.
So the WGB, you means for the wine gap?
Pardon? One more time, please.
This 275 nanometer emission is, can you control single peak?
No, 275 is not emission peak. This is excitation peak from the gadolinium T plus ion. Actually, emission peak is 311. So let me show you in this. Yeah.
I see. So it's also UV, right?
Yeah.
311 is also
you can
UV.
See UV. Yeah, you can see the pink line. You can see my arrow, right? The pink line.
Yes.
This pink line. The pink line is without tungsten. Just only gadolinium and borate glass. Without tungsten, that means you cannot observe. You can see the blue line. You can observe the very broad peak. Start from 250 to the 350. This is the broad peak. It's come from the tungsten and oxygen charge transfer. So if you don't have tungsten, you can easily observe clearly the two bands from gadolinium T plus in this region. The first one is 275 and second one is 311. That's why when we excite at 275, you can observe 311 by down conversion emission in this work. in this left picture, but 311 is very low because most of energy is transferred to the SM. That's it.
I see. Because this 310
Thank you.
nanometer has a lot of industrial application, even medical science. So I was just thinking that this emission spectra is quite interesting. Anyway, thank you for your comments and kind explanation.
Yeah. Thank you so much. Yeah.
Yeah.
Let me give some information to share with the research friends. So actually, if you do only the single doping, like the GD doping,
okay.
Yeah, not another luminescent agent, just a host. Your host may be polymer, glass, single crystal, and so on. But you put just GD doping, a little bit GD, not too high concentration. You can get the same emission because GD is a FF transition also. When you excite 275, 310 is always coming out, but the intensity is depend on your host. You have to investigate and optimization again. But pattern of emission is the same from GD.
I see. Actually, I'm working on 3.5 materials for UV LED, but this is quite interesting work, what you show. My just comment is that if you can produce a single peak by doping or whatever, new research, just to get emission peak in your this glass research or whatever material, it would be very interesting for the future industrial applications. So mercury lamp is using for UV light, which is toxic based on Minamata convention. So that's very interesting. Anyway, there's just comments in a lighter mode. If you can control just single peak, not a two band, but of course, one is the excitation, but another, if you can get a single peak UVB light, would be very interesting.
Thank you so much. So I can share some the result to you. So please.
Yeah, of course. So my name is Ajmal.
Thank
just
you,
skip
Professor.
in. I have tomorrow talk, so we can talk tomorrow. I hope so.
Yeah. Very nice.
Thank you. Okay. Bye-bye.
Thank you so much.
Yeah, pleasure.
Okay, thank you. I think if we change the dopant, for example, GD and cerium, we can obtain the single peak, GD 311 emission peak, single peak, and cerium 346 emission. I think we can achieve this by changing the dopant. Are you pick my point, sir?
Hello.
Yeah. Hello, please.
Yes, sir.
Yeah, I think, it's interesting. So I saw you people belongs to the same groups. So yeah.
Yes, sir.
Just try to make it possible in a more single spectrum. I mean, just to reproducible would be very nice. It's just my simple comments. Yeah.
Yes, sir.
Okay,
sir. Thank you, sir. Thank you. Any other questions, sir? Any other question? Okay, sir. No question. I have a question, sir. The ordinary samarium emission is 602, which is, I think, orange line, and your material is 647. So the application of this emission peak for detector purposes or for LEDs or for which purpose, sir?
Pardon, what is your question? One more time, please.
My question is that you see in this picture 600 nanometer is the emission peak of samarium. Okay, sir. You show the next slide, 646 emission peak is maximum than 600. So we can choose this one for detector purposes. 647
actually the detector in each peak is also important. So two things is you have to concern the one of the teeth rings. The most important one is intensity of light. I mean number of photon is coming out. That means the strong of the signal when you want to use for detector. Second one is the decay time. Decay time is depend on your application, because sometimes you have very fast decay time like the cerium doping in the like the nanosecond decay time or picosecond decay time, because of your flux is also very strong and you cannot make a good counting system. So decay time is also important. For the light is also important, but I think the important is less than intensity of light and decay time. The wavelength of emission you can decide. For example, what kind of the material you want to detect that wavelength, you can choose the appropriate the light detector and amplification system in your detector. Like you can choose your appropriate PMT, a photo multiplier tube, or the photodiode in this case, and also for your application in future. I hope this is
Okay.
the
Yes,
good
sir. Okay, sir. I
answer for
got
you,
it.
Dr. Falak.
Okay, sir.
Yes.
Okay, sir. Okay, sir. Thank you. And I suggest that please, if someone interested in collaboration with your lab or with your groups, so please let's talk about that how can collaborate with you. If Women University Multan want to collaboration with you, or someone other wants to collaboration with you, so what's the
Yes.
procedure? Yes.
Yes.
So what is the procedure to
Hello.
collaboration with you? Yes, sir.
Yeah, just email and we can talk. That's it. We can talk
Yes.
first. What kind of the collaboration? Like
And
now we also many work with the, I mean in progress with to the Dr. Falak, to the Dr. Kuro and his team in Aquam also. So please
yes, sir.
email first what I can help on, what I can work together. We can share idea and work together, because we also stay in different field. Some simple work from my field may be very good work for you. Some simple work from your side may be very good application from my group. If that's why we need collaboration. That is very important.
Okay, sir. Okay, sir. Thank you very much once again. And I am
Thank you very much.
handed over to, yes, sir, handed over to Dr. Malikarani to online campus, on campus. So, okay,
Yes.
thank you very much. And Allah Hafiz.
Thank you. Bye bye, everyone. I will stop my sharing slide.
Okay, bye
Okay,
bye.
okay. Okay.
Yeah.
Bye bye.
Thank you for all questions.
ओपन डैशबोर्ड में ओपन है, इसको जस्ट शेयर करना है। थोड़ा डाउनलोड स्लो करिए, अभी डाउनलोड
Hello everyone, Assalamu alaikum and good morning. My name is Muhammad Salman Hadar and I'm currently working as an assistant professor in chemical engineering department, University of Gujarat. So today I'm here to present my work and our research group work on the synthesis of membrane, water treatment membrane, which we have been working on from since 2014. So these are the contents of my presentation. We will start with the main issue of Pakistan, which is recently that was presented in our national water policy. And then we will go through our overview of our research, then membrane and future research. So what is the main issue? In 2019 and 20, our government presented a national water policy. And the main focus of that policy was the total points around, there were 12 points. And I will present some of points as my main concern. The first one was, the most important point was the trans-boundary developments. That was what is happening in India, because all of our rivers, freshwater rivers, were coming from trans-boundary. So recently there have been some developments by our neighbor, They are building some dams which will reduce or probably lower the underwater level of the water. And this is a main factor that in 2015, World Health Organization has presented that in 2025, Pakistan will be a water deficient country. And we have only 4 years. So this was the main point. And the second one was the depleting underwater ground quality. And then growing conflicts between the different areas of our country, because the distribution of water is different in lower Punjab, lower Pakistan and upper Pakistan. So all these points, including the national food security issues, they were directly related to the water quality. So to present these main issues of our national water policy is that from we started working on membrane sciences since 2014. Up till now, in our country, in Pakistan, we don't have any brand of a membrane or any company that is manufacturing a water treatment membrane indigenously. So our focus was to develop our product, because we are depending on USA. There was Hydroline and Dow Chemicals. We are importing our water treatment membranes. Actually, those membranes are RO membranes and nanofilter membranes. So we are importing from USA, Korea, China, and other countries. So we are totally dependent on them. Recently, because of this pandemic, the import was disturbed, and even the water treatment membranes were not allowed to enter the country. So for a very short period of time, we were in water crisis. And why we were in water crisis? Because we did not develop our own membrane company or product. So there is no product presently in our market which is indigenously prepared. So our focus of this research is to develop a product or a domestic membrane which can be used in households, or probably in future we can develop a membrane which can be used in industries for water treatment. So this was the main concern of our country. And just to revise one thing, that in 2015, Pakistan will be a water deficient country. So let's move on. So what was our research? Okay, our main work, and it was published in 2016-17, was to develop a membrane, a nano filter membrane, and we were successful in developing one. The main focus of that membrane was to increase the life of a membrane which is already present in the market. And what we did was, we actually encapsulated, initially we encapsulated the silver nanoparticles, but that work was already presented in the world. And what we did was, we coordinately immobilized those silver nanoparticles onto the surface of the polymer. And we used polyether sulfone. And polyether sulfones are a basic polymer which is used for water treatment membrane. So what we did was, we increased the membrane life almost 4 times the life of a membrane which is present in the market presently. And what we did was, we remained under the World Health Organization standards in release of the silver ions. Because when we attach the silver ions on the surface of the polymer, whenever the water is, the silver nanoparticles are immersed into the water, silver ion is released. And the amount of that silver ion must be regularized and standardized. And the World Health Organization standards, we remain under those standards. So I will introduce briefly about the concerns we have in a water treatment membrane. This is a water treatment membrane after a use. You can clearly see it is a domestic water treatment membrane, and a lot of dissolved solids which are stuck on that membrane. They increase the pressure on the pumps, and initially, and the cost of the water which we drink increases. And these dissolved solids are basically known as biofouling. They also include inorganic fouling, organic fouling, and particulates. So in Pakistan, we have the groundwater quality is very improved, but recently, because of some industrial impact in specific areas like Faisalabad and other like even like Multan, the water quality, underground water quality has decreased. Amount of suspended solids, amount of dissolved gases, amount of inorganic materials increased. So in order to reduce these fouling on the membrane, we incorporated with silver nanoparticles. So what we did, I will first introduce what is biofouling. So as we all know that okay, little technical problem. Okay, we will start with the first step, that water, as we know, water is a universal solvent. So it contains all kind of biological, inorganic and organic materials. So most important thing is first that microorganisms are always present in the groundwater. So we cannot eliminate them inside the water, like inside the channels, underground channels. So we can only fight them on the surface of the membrane. And it starts with when microorganisms attaches the surface of the polymer membrane, it starts to produce extra polymeric material. That extra polymeric material is actually, it has two main functions. The first one is to attach that bacteria to the polymer surface, and the second one is to they are always reproducing and increasing their number, and also they are producing their own food. So that polymeric extra polymeric material gets attached to the membrane, the nanopores, and starts choking all the pores, and eventually the pressure on the pump increases. So when the initial growth starts, the size of those clusters starts to increase. And okay, I will explain here one most important thing, which is water is a universal solvent, and it has all kind of dissolved solids in it. So what is the purpose of this bacteria? It starts to utilize those dissolved solids, all the dissolved contents in that water, and producing and immobilizing them after generation of the energy, immobilizing those materials which were dissolved in the water onto the surface of the polymer. So the nutrient problem cannot be solved because water always contains those solvents, and we cannot undissolve them. So when those dissolved contents come in contact with the bacteria, they utilize it, and this is I mean infinite. They will always get those dissolved solids to grow. So continuously getting those nutrients, it will start to increase its size, and then it will start reproducing and producing more bacteria. And eventually you can see in our previous slide that the membrane starts to choke, and the quality of the water, the price of the water starts to increase, because membrane will work because it has different levels of we have different levels of membrane in a single, you can say, a single cell of a membrane. So it will produce water with high pressure, and the cost of that water, which right now in Pakistan is for 1 liter, is around almost 40 rupees. It will increase up to 50, 60, and 70 if the pressure on the pump increases, because the cost of energy increases. So this is our initial work. We started with the polyether sulfone membrane, as you can see, PES, and we nitrated it to produce some bonds on the surface of the polymer. After treating it with nitric acid and sulfuric acid for a specific period of time, we were able to produce some bonds on the surface, and they were nitrates. And after treating it with SnCl2 and some other precursors, we converted those nitrate groups into amine groups. And amine groups were then used to attach the silver nanoparticles. We reduced the silver nitrate and onto the surface of the polymer membrane. And you can see in this diagram that those particles were attached, immobilized, more precisely, and with the bond that is coordinate bonding. We immobilized those particles on the surface of the polymer, and those particles then released silver ion. That silver ion then attacks the lipids of that microorganisms, and then enters into the body and denature the DNA. So this was the procedure of disinfection of those silver nanoparticles. So this is our membrane, and we have a patent for this membrane. In terms of chemistry, this was the formula of polyether sulfone. And you can see in previous diagram, I explained with the block diagram, but in this one, I will explain with the equations. The polyether sulfone, a polymer which was first nitrated with nitric acid and sulfuric acid, you can clearly see that we got our nitrate group on, I think it's ortho position. And then we reduced it with the sodium borohydride, and we converted those nitrate into amines with tin chloride and sodium iodide and HCl, and we were able to convert those nitrate into amines. And amine is a very good good for bonding with silver metal nanoparticles. You can see all these steps that were involved in our research. So now we should go on to the results that we got. This is the first results, FTIR of that polymer. You can clearly see at around 3,478. We did analysis of 4 samples. The first one, you can see A is a pristine polyether sulfone membrane. It's just pristine polymer. No chemical reaction or no processing of that polymer was done. And in the second one, we did nitrate. This the first step of the previous slide. Nitrate attached on the surface of polyether sulfone. And next one was the third step, amine attached on the surface of the polyether sulfone membrane. And the last one was the silver nanoparticles. So you can clearly see in C and D, there is a shift in the peak. That shift indicates the formation of the coordinate bonding. And this was also reported previously, that if a shift happens about for a very small wavelength, it clearly confirms the presence of coordinate bonding. So C and D clearly you can see from when a nitrate was introduced, amine and silver nanoparticles were formed. We can see shift in the peak, and that confirmed that the coordinate bonding is present. So we move on to our next analysis. What we performed was XPS analysis, and you can clearly see, NMR and XPS analysis. NMR can clearly tell you that there's a presence of nitrate and the presence of amine group. And we confirmed it with the NMR, and then we move on to the broad spectrum of surface spectrum of XPS. In surface spectrum of XPS, you can clearly see in A, B, and C. We did not perform the nitrate group in this one. Sorry, we did not perform the silver nanoparticles, the last one, the D1. Silver nanoparticle attached on the surface. We did not perform the XPS of that one because we did not require it. You can clearly see in A, this is a pristine polymer, and we can see C1 and O1 and this sulfur group, which is present in polyether sulfone. And in surface spectrum of the nitrate and the silver nanoparticle, the third one, we can see there is a peak of silver in Ag3D, and in nitrate we can clearly see the presence of N1S. So we increased the spectrum. Sorry, we zoomed into the spectrum. Okay, I think that slide is missing. When we zoomed into the spectrum, we were able to, you can see this is surface spectrum. We also have a broad spectrum of all these orbitals. Those analyses clearly tell us that what kind of environments are present in after decongulation of those peaks. We can clearly see the environments present in the curves. So here we have actually the composition of the membrane. I think we should have this slide up at around 5 or 6 slide. So we had M1, M2, M3, and M4, as I previously explained. M1 was a pristine polymer. M2 was PES attached silver nanoparticles. M3 was amine polyether sulfone, and the third one. So these are the images of the SEM that we had, and you can clearly see this is we can see a typical image of a RO membrane or nanofiltration membrane. You can see a finger-like structures. These are the nano channels from which water flows, and then these channels starts to shrink at the top. At the bottom. After when water starts passing from the broad channels, it moves towards the shrink channels, and then the quality of the water improves. And this is the typical image of a water treatment membrane before the treatment. After treatment, all these channels and the porous channels are choked after use of 1 month, or it depends on the quality of the membrane. Once again, I will tell you that this is a typical, these are the typical finger-like structures of a water treatment membrane. So in order to check or confirm our experiment that we did on this membrane, we zoomed in. As we zoom in up to 5 micrometers, you can clearly see a porous structure of that membrane. All these channels from which the water flows are interconnected with each other, and all the filtration, all the dissolved ions and dissolved solids, the filtration of those solids happens here. These porous structures are in billions, so they act as a filter, a primary filter for water. So you cannot see silver nanoparticles at around 5 micrometer of. If we increase the resolution, now we can clearly see that silver nanoparticles are attached on the surface of these membranes. This is a pore from which a water molecule passes, and you can see layer after layer. These pores contains silver nanoparticles uniformly distribute on the surface of the membrane, and this was our success, and this is actually our patent. So these previously, I will explain some previous works which were presented in around 2015 and 2014. Some researchers from UK, they incorporated the silver nanoparticles. They just mixed those silver nanoparticles in the matrix of the polyether sulfone membrane. They just mixed it, and then they solidified the membrane using in wet inversion technique. And these nanoparticles were encapsulated with the polymer. So that encapsulation actually prevented them from releasing that silver ion. Without the release of that silver ion, we cannot achieve our antibacterial effect. So what we did, and we were successful in that we attached those silver nanoparticles not inside the matrix, because that will be encapsulation of those particles. We attach them on the surface of those that polyether sulfone membrane. So in this diagram, this is our main work. You can clearly see the silver is attached and also one more very important thing, that the best size of the silver nanoparticles to produce its antibacterial effect, the best antibacterial effect is at around less than 20 nanometer size of that silver nanoparticles. So if the size of the silver nanoparticle increases above 20, the effect of the antibacterial effect starts to decrease. So this is around 200 nanometer. You can clearly see the size of the silver nanoparticles. It's around 20 and less than 20. Even we have some nanoparticles around 5 nanometers, which are very efficient in antibacterial properties. So let's move on to the particle size distribution that we got. And you can see here, this is the percentage on the y-axis. We have around, if we add up 35 and 3, we have more than around 50% of particles less than 25 nanometers. So this is the best result that we got from M3 and M4. And this confirmed, and this concluded that the experiment what we did, the idea what we had was finalized. And here we also have a thermogravimetric curve, TGA curve, and there was not a difference between the membrane present in the market, which is M1, and the membrane we developed. So there was no difference between their strength or other properties, no difference. So now the final experiment what we did was we also studied the release of the silver ion. We did it with the ICP, and we calculated what we did was we calculated the static release of silver ions. We poured that membrane, the sample M2, M3, and M4 inside a deionized water, and we start the stirring, and we used Millipore membrane, which is available in market. Millipore is a very good company which produces membrane, nanomembranes, and we encapsulated those samples in that membrane, and we started the stirring for 10 days, 10 to 12 days. After the stirring of 1 day, silver ion was released into the deionized water, and we collected that sample and we sent it for analysis, and we got these results. You can see in M2. What is M2? M2 is the membrane which contains which contains just mixed silver nanoparticles in the matrix of the polymer. So it has very large amount of nanoparticles, but they were not attached to the surface. So you can see a very intensive release of the silver nanoparticles, and that release is above the World Health Organization standards. And our membrane, you can see in diagram, the second one, you can see all the release of the silver nanoparticles were less than 30 milligram per liter per hour. So we remained under the standards of the World Health Organization, and the silver ion release was very good. And finally, the result of the membranes M2, M3, and M4. So at the day 1 in M2, 30% of the silver was released. So the silver started to deplete starting day 1. And M3 and M4, which were we have taken for membrane 3 and membrane 4, 6.6% silver was released, and M4 6.25%. And in day 6, almost 82% of silver was depleted in the membrane, which is presently available in the market. And the membrane we made with coordinate immobilizing of the silver, 44% and 53% silver was released. And if even after 12 days, we have 63 and 71% of silver present. And you can see around day 7, 8, and 9, the M2 membrane was totally depleted with the silver nanoparticles. So let's move on to next slide. That is the reaction kinetics of the silver ion. We got that the process we had in our hand was a first order reaction. Silver ions were continuously released, and it depended on the concentration of the silver nanoparticles. You can see with the regression that we have 0.96, and it stated that it is a first order reaction. Okay, this is the final analysis that we performed. This is a sample of a round sample of a membrane in M1, M2, M3, and M4. And we performed was antibacterial effect. The experiment is known as zone of inhibition test. Sorry. And in M1, without any silver nanoparticles, you can see the bacteria is growing on the surface of the membrane. And M2, which was in that membrane, we just mixed the silver nanoparticles into the matrix of the membrane, polymer matrix. And you can see the zone of inhibition is around 2.5 millimeter. And now comes M3 and M4, which were our patent. You can clearly see a zone of inhibition of around 5.5 millimeters and 4.4 millimeters. A very good antibacterial effect was produced by those membranes. So let's move on to the conclusions. We were able to immobilize the silver nanoparticles onto the surface of the polymer, and also enhance the antibacterial properties, prolong the silver ion release. Membrane surface modification were also performed, and I will explain in the future work in the next slide that what we are planning to do. And the main and the final conclusion was we increased the life of the membrane 4 times of the membrane which is present in the market. So also our future work is to work on, because we have a very good pattern of silver nanoparticles uniformly distributed on the polymer surface. So what we are trying to do right now is we want to produce hydrophobicity inside the membrane, which can help reduce the pressure on the pumps of those treatment units. So presently we are working on it, and also our work you can see this in this diagram, that the channels contains silver nanoparticles uniformly distributed, and these patterns we can use these patterns to reduce the friction between the water and the surface of the polymer. So we got some very good results of you can see M4, that the angle is very good. It also says that the membrane is hydrophobic, and M2 the angle is very high angle we got, and this shows that the membrane is hydrophilic. So these are the results that presently, this is the research that we are working on right now, and we are going to present it inshallah in a very good journal. So this was the work of our research team, and we are trying to manufacture our local and indigenous product to be launched in the market in Pakistan before 2025, because in 2025 Pakistan will be a water deficient country, and we need those membranes, not from USA, China, Korea. We need to develop our own membrane, a local product that can be used in domestic household as a domestic household item. So these were my latest work, and if you have any questions, I will be very happy to answer. Thank you very much. Any question? Yes.
That's a good to manage the parts. I have a query about because you said how to say specifically that these membranes are 3 to 4 times better than in the market, and you are going to launch it very soon. So do you have I'm a little bit critical of this topic.
No problem. No problem.
The problem is that many people I heard many talks in Pakistan. And most of Pakistani people say after the research of they say that we have got this wonderful and this and that. But in the end, do very much nothing comes out of that research. So do you really have a plan that you are going to launch your product in the market, and how? If you really have, please let me know.
Exactly. Initially, we will start with a simple membrane, because this is the research that is under process right now. In order to allow it to come into the market, we have to go through a lot of certifications and other things. But presently, we are trying to get funding from HEC and other organizations to launch.
How much money is required?
Initially, we are planning to make the main machine involved in this process is industrial applicators. So we are trying to import it from China, and then we can rebuild indigenously in Pakistan, because applicator is not that like rocket science. It's just an applicator which can adjust the thickness of the membrane. So we are working on it right now with the NRPU and other fundings. But initially, as you said, we will start with a simple membrane that will be produced with a simple wet inversion process, produced all over the world with the wet inversion process, because it's a patent. The process is patent. But we will start with this one. And I know that I previously made that membrane with wet inversion process, and we can make that membrane and allow it to come to market. This research can go, we can extend it for around 6 years, because we cannot allow this work to come into market without any certifications, because we don't know what will happen to the consumers, because also we have silver nanoparticles and what will the amount. This is only a research, but we are working on it. We are working on a simple membrane, which will be produced with wet inversion process. So initially we are working on that. And you're right that this research, we have claimed that our life, and also the result shows that the life of the membrane is increased. But right now we don't have any certification. We have a patent, but we don't have a patent. Yeah, and we don't have a certification for a consumer. What will the effect of this silver nanoparticle on the health of the consumer? So we are working on it. Thank you. Any more questions? Yes.
I just want to ask about the mechanical properties of treatment. Because you have mentioned the few modifications you have made already. So, sir, is there any chance to add some matrix with the membrane, any porous matrix, just to increase the mechanical properties on the stability of the membrane?
Yes, recently I have published a paper and I have not included this one. What we did was we produced silica particles, porous silica particles.
Yes, that was actually
Yeah.
I was.
So we use those porous silica particles as a scaffold for silver nanoparticles. The porosity of the membrane increased, and also the mechanical strength and the ability to withhold the temperature, high temperatures increased. But also this is all we have published it, but still it's not applicable on that level as Dr. Dr. Punjoya said. We have published it.
Right.
And also, I will show you some results about TGA. You can see clearly in TGA, the black graph is a pristine membrane which is already present in the market, M1, and the membrane we made is 3 and 4, blue and green. There is no difference in TGA analysis from the one present in the market and the one we made. So there is no difference. Any more questions?
Yeah. Yes, I have one question. Yeah, very nice talk. Can you hear me? This is Ajmal from Japan.
Yes, Professor, I can hear it.
Okay, so it's very nice talk to purify water and kill bacteria and make it more useful for society. But where is the end point and bottleneck? I mean, your research is going to be how you will materialize. I mean, in terms of to use for water filtration for people. I mean, in Multan, I would say, for example, for instance. So, how you look into this matter?
Actually, Professor, in Multan and most of the country cities, the quality of the water is not that good in terms of we can say microorganisms. In Pakistan, it's very big problem. So
yeah, it's not only microorganism, but also a lot of microorganism and microbes and bacteria and many things. Anyway, okay, go ahead.
Exactly. So presently, right now, we are also working on inorganic dissolved solids. But in Pakistan, our biggest fear is outbreak, which is cholera and other waterborne diseases. And we do not have a very good water sanitation system. Our underground pipes have a lot of like breaches. So I think this research with this, I don't know right now about the cost of this membrane, but it can increase the health standards and also reduce the outbreaks. This is the main focus, what we can say about for this research. It is not.
I mean, like you say, you will do some indigenization for your research to make it a product, right? Am I right?
Yes, exactly.
So how you can you briefly explain to all the people participant, including me, how like this product will be used just for house utility at some water, where's the water coming from the well, or you will make it possible with the government, with the city hall people who provide water to the big city. So I just want very simple, not the technical detail, the membrane or at the atomic level, how you make these silver-based particle things. But I want your product, where you will use, I mean.
Yes, Professor. As I mentioned previously, in Pakistan, we have some a specific system. In order to produce a commercial product, we have to go through higher education funding, because right now we are doing it. Initially, we are going to avail a technology development funding from HEC. In that process, we cannot produce this membrane, the membrane with the silver nanoparticles, right? Because we have to get some certifications and other stuff. But with the technology development funding, we will be able to produce a membrane, a commercial membrane. But initially, that membrane will have no relation with this research. It will be just like a wet inversion process membrane, which is present in the market right now all over the world. We are importing that membrane. So what we are doing is like we want to be independent from the world in producing, because India has almost 5 companies that they are producing their indigenous membrane and household membrane. Every house in most of the areas where the water quality is not good, they have a RO plant in their house with a membrane that produces almost I think 50 gallons a day. Flow rate is very low, but they have the membrane. They have developed it. They have a patent for it. But in Pakistan, 100% of membrane is imported. 100%. We have membrane from USA. We have membrane from China.
Okay.
From Korea. So we just want to become independent in that field. And in future, with the R&D, we can produce our own patent, because we have a patent for this one. We can produce it. We can commercialize it. But in future, not initially, we will start with the simple membrane. Inshallah.
I would just in the lighter mood, I would say that you are connected with somehow with the water purification and cleaning. It's very good for the because I know that more than 30% children dies of the waterborne disease, according to the World Health Organization report last year. So it's very delicate issue. So you better, just my recommendation, to make all those research in line with the UV light industry, ultraviolet, especially UVC light. In your university group, you can introduce some research group to work on the UV light treatment of the water and to get some data in the future. And I attended last year one conference later, and I can share with you this platform, which is the world standardized groups from Canada and Japan, Germany, and they are working how to clean the water for City Hall, for the big cities. So, of course, your technique is wonderful. I appreciate your efforts that you are doing in Pakistan, a country where we have limited resources. I mean, in terms of research fundings and industrial support, I know. That's why my simple recommendation at this stage, to make a complete package for some small families, for recommendation for the big cities, like Gujarat you are living, to how to make the water more clean and drinkable for common men in the street. And that will be very interesting.
Thank you, Professor. Thank you. Just wish us Godspeed. We are working on it, and we will produce in near future. We will produce a commercial product, inshallah.
Okay. Yeah. Good.
Thank you. Thank you. Any more questions?
There is no questions, but we want to tell you that we have also synthesized some silver chromate systems, spinel systems. They are nanoparticles and they have very good properties. Students, and they're going to publish that work. So we would like to collaborate with you.
Okay. Yeah, we are ready. We are ready for collaboration. Yeah. Highly toxic. It's a carcinogen, level 3 carcinogen, level 2 carcinogen. Little bit problem.
Yeah, chromate systems and spinel chromate systems.
Yeah, we also have results for the flux, water flux, salt rejection. But right now we have not presented because we have published in another journal. So the one you are talking about, we have done that one. Actually, the problem was the dead end cell. We don't have that one in Pakistan right now because we have in our lab, but we are trying to make our own dead end cell. Dead end cell is wrong. Yes. No, we don't have. We don't have dead end cell. Okay, I think we should conclude. Thank you, everyone. Thank you.
New share करना। समय ठीक होना। Busy you. Chemistry, Dr. Naeem. Yes. बस ऐसे सर वो मैंने रजिस्टर कराया था, उसको गई थी, फिर वो एकेडमिक का आ गया। आपको पता है पेटेंट ऑफिस वाले क्या काम करते हैं ना, और फिर रजिस्ट्रेशन।
मेरे भी सुबह नींद से बात हुई थी।
जी सर।
मैं देखूंगा शायद अगर मैंने प्रोसेस
बिस्मिल्लाहिर्रहमानिर्रहीम। I am Dr. Saadat Nadeer, Associate Professor at Bahauddin Zakir University, Multan, and I thanks all the organizing committee for the International Conference on Global Challenges in Sustainable Energy and Environmental Development, organized by Women University of Multan. And my research topic is rapid and low cost smart sensor for energy, environment, and biomolecules. I will share some of my work, which is recently carried out in my laboratory, and I will share the 3 examples into the one in the energy and one example for the environmental application and one in the biomolecules detections. Sensors, what are the sensors and what are the smart sensors? Sensors, why they are and why we use them and why we need them. Sensors are the devices that measure the physical quantity and converts it into the signals which can be read by an observer or by an instrument. Trend for the smarter, multifunctional, rapid, low-cost sensors. This is used for the reduced size and the weight, performing the sample handling step together with the sensitive analytical measurements. Smarter sensors have also been widely used to acquire and the process data to be used in the assisting with diagnosis, self-diagnosis, telemedicine, home monitoring, and to save the lives. Therefore, this is most important. And in the COVID-19, you can see there are the many sensors which has been needed. That is the thermal sensor you uses at the doorstep for the temperature measurement of any body, which is entering into the home or in any building. And there are some other COVID-19 sensors that are used for the detection of the antibodies into the blood. And the sensor actually, what are this sensor? Actually, these are the transducers. And what are the transducers? These are the devices which convert one form of the energy to another form. And these are consisting of the 2 parts, sensor and actuators. Sensors actually converts the physical parameters into the electrical output, and the actuators actually converts the electrical inputs into the physical outputs. And there are many different kinds of the sensors, but there are some challenges and gaps in the sensor applications. These include stability of the chemical sensors, mechanical sensors. For example, for chemical sensors, continuous exposure to the biofluids may lead to the biofouling. Chemical changes are irreversible, non-specific adsorption on the transducer surfaces. You also have seen that in the COVID-19, during the COVID-19 pandemic, many people has complained that strips don't gives you exact measurements about the antibodies that are produced into the body. And that depends upon how we are handling those sensors strips, because handling for the every person is different. Optimizing accuracy, sensitivity, and specificity of the sensors for the rapid testing improving the reproducibility and scalability of the manufacturing the sensor devices. And most important is the limit of detection of the sensors. And this limit of detection, you can also see into the antibodies detection into the COVID-19 patients by the strips. Capable of simplifying the sample preparation step, improving the efficiency manufacture of the disposable, low cost and high efficiency sensors. Similarly, developing the accurate and robust biosensors integrated with the remote control system for environmental monitoring, and improving the robustness and accuracy of the biosensor for agriculture applications and quality control in the food industry. There are some of the everyday applications of the sensors we can see around us. These are used the color sensors. This is the heartbeat sensors. This is the rain sensor. This is the smoke sensor. This is the alcohol sensor. This is a water flow sensor. And suppose you can also see the touch sensor you can use at your mobile, IR sensors, IR detectors. These are the different sensor types which you can use on a daily basis. And for example, this is the soil moisture sensor. This is used for the agriculture purposes. How we can fabricate or integrate smart microsystem or the sensor at lab at the small scales. There can be used some materials. We are usually using in my lab, so I have explained only the three parts: glass, polymer, and the paper. Glass material, this is a well-known and the cost-effective material. Moreover, it is transparent and biocompatible material. And for example, this can easily commercialize component. Similarly, if we use the polymers, this can be the cost-effective as well, easy polymer processing, flexibility, this gives the and versatility, transparent. Similarly, if we use the paper as a sensor material, just like you see around us in your pharmacies, and from a ecological aspect, this is the cost effectiveness, printable and stackable and filtering properties. So these materials can be used for the integration or fabrication of the sensors. Number one application that we are using in our lab, and we are working over this one. Number one application, this is I'm talking about, this is the energy harvesting smart sensors. One of the students group is working over the harvesting smart sensors. Energy harvesting, actually what is, it is the process by which the energy is derived from external sources, and external sources anyone, that can be the solar energy, thermal energy, wind energy, salinity, radiant or kinetic energy, that can be captured and stored for the small wireless autonomous devices. And what has motivated this one? This is not the new technology. This has been taken decades back, and this can be many people has taken this one for the new energy harvesting devices for to power the sensor networks and the mobile devices without the batteries. And we have the energy harvesting is also motivated by the desire to address the climate issues and the global warming issues. So some of the sources and example of energy harvesting we can see, or we have listened on different medias, how we can generate energy at the smaller. This is very simplest example as well. Sometimes some fabrics, when they are moved to each other, they produce some electric current. And this is the energy harvesting. Waste energy flow harvesting method. Water is passed through the tubes in the tank. That is the triboelectric nanogenerator that rotate the shaft to which the material and fans are attached, and therefore shaft moves the material, creates the opposite polarities that flow the current. And another example from the literature is the textile energy harvested method. In this, the energy is harvested by the movement of the human body. As the human body moves, opposite charges are created between the skin and the clothes. Therefore, the energy can be harvested. In this process, we can use the silicone and polyester material for the preparation or for the fabrication of the dye. This is some of the examples you can also see at the social medias or around your news, in the scientific news. I will talk about the triboelectric nanogenerator energy harvesting devices. This has spread and developed with the advent of improved tank designs and employment of various functionalized materials. Tank devices offer plenty of characteristics as compared to other energy generating sources and sensing devices. For example, these are the smart, these are small, these are thin, these are flexible, versatile, and we can add it to different references for this one. And what are the main function or mechanism on which the TANG or triboelectric nanogenerator energy harvesting devices work? There are the 4 basic principles. That is, number 1, contact separation mode, sliding over mode, single electrode tanch, and suspended tanch layer mode. So my group is working on the contact separation mode. We have just started on the interest of some of the students, this work, tanch energy harvesting devices, how they can be fabricated. This is an attractive, powerful technique for the self-powered mechanical energy harvesting. Triboelectric nanogenerator form the low-cost and easily available material. The devices consist of the novel combination of the PTFE waste bottle pieces as a substrate modified with the aluminum and graphene oxide materials. In this work, students has used, our group of members has used only the waste bottles as a substrate material, plastic waste bottle materials. They have cut into the different shapes and they have designed the harvesting energy device for this one. And this is my students who have worked over here. This is Sayyid Brasa Nikwe, Fahad Ali, and Tosifam. They are working and they have worked about this field. They have choose this field because self-powered energy generation is the need of the hour, and to reduce the emerging plastic waste. And they have focused the plastic waste as a substrate material for the manufacturing, for the fabrication of the sensor. And they want to create the alternative energy sources. So they have tried a little bit in their lab with the limited sources. So I will present some of their work, which has done one work. This has been the overall material and the combination and the circuit, and that is the charging and discharging of that material they have designed for this one. Okay, this is this one. I explained the further this one. This is the tank assembly overall. This is the contact separation mode. When we press this one, the current is stored, and when we release, then the current is flow, and then that is measured by this one. So this is the contact separation mode methods. They have used this one. In this, they have used the PTFE substrates, aluminum foil electrode, and graphene oxide materials layers for this one. And I will show you the step by step how they have used this one. My research members use this plastic material, plastic bottle. They have cut it into this shape where you can see into the picture. That is the PTF. One side they have overlapped with the PTFE layer, and then is the plastic bottle place. This is our ordinary plastic bottle, water bottle, and they have connected this one with the electrical connection and use the cyclic electrochemical workstation potentiometry, and they use this one time and the current. By this one, this is just when pressing this one and then releasing this has this results, and they have produced 0.003 milliampere current. This is very small amount, and because this is our blank one, they have considered it to the blank one. And so next step they have to do this one. They have inside aluminum foil on the one side and PTFE on the other side on the plastic bottle pieces. They have, this has been randomly, they cut this one into the different sizes, and they have many experiments. So this is one of those experiments. And with this aluminum foil and one on the other side PTFE foil, when they have experiments over this one, that is the pressing and then releasing, they have the 0.005 milliampere current that has been produced by these results. You can see into the picture. And next, they have modified further this structure. They, on the other sides of the aluminum foil and the opposite side, they have coated the graphene oxide and again do the experiment. And then they have, then they were successfully in producing the 4.5 milliampere currents. And that is the 50 folds high frequency as compared to without graphene oxide molecules. And further this one, they have used the former results. These results are from the single unit. That is only one piece of this one. These results are due to the double units, and that is 2 units they have, and the current amount has been doubled. That is 4.5 to the 10 milliampere current has been produced. So as they have suggested that they have experimented over this. As we increases units, the amount of the current replicate with each year with this one. Similarly, they do some of the perimetric charging and discharging of the tanks. So they have designed for this one in our lab. So they have completed the circuit, this one, and they, with the double, they have used the charging and discharging curve. So you can see this is the chrono and pyrometric results for the 200 seconds and interval time 0.5 seconds. So this is the example for this one for the energy, and I will share another example into the environmental samples. Some of my students, they are working, and we are working into the smart sensor for environmental applications. This is our published work in 2021 in January. And this is just one of the membrane separation, and we have used simple chlorophenol. This is some pesticide from the industrial wastewater that has been and this is a already published one. And I will discuss some of this one. I will choose one of the pesticides, OP pesticide, that is the organophosphorus pesticide that are present into the environment, into the soil, into the water, and into the air in the agriculture land areas. And how these are degraded into the environment. This chloropyrifos, for example, one example I'm giving you, they have many examples for this one. Chloropyrifos exons, this is converted into this one. And this integration or degradation causes the inhibition of the cholinesterase enzyme that is produced into the human body. And then this can also be degraded into the trichloropyrifos, diethylphosphates, and then it is also further degraded into these products and causes the gluconide and the sulfate conjugates. So this is one of the degradation, therefore we use this one. This is our work. We have designed this one. My student has make this graphical abstract for this one, overall procedure, but we want to do this one. In this work, students has used the optical sensors. They have decided to fabricate the optical sensor with the very low cost materials, and very easily they can be done. This work can be done very easily. In this OP pesticides, this is the sources. The OP pesticides can be obtained from the wastewater, and these are present into the air. This is present into the food, and these are biotransformed into the human body, and this causes the many diseases, for example, oxidative stress, neural injuries, and the viruses. And so students, our group has done this one, that is the blood sample analysis and paper-based analysis for the water analysis. So I'm presenting one of this one, a few work for this one, water analysis for OP pesticides under the sunlight and under the UV light. So we can see the clear, this is the just graphical abstracts, and this one. What is the basic mechanism they have choose for this one? They have used the acetylcholinesterase enzyme, cholinesterase, and they have the different combinations, silica content dots and ACHE pesticides. Then the choline is produced in the presence of the pesticide, degradation occur, and the color of the silica quantum dots, that is into the greenish yellow, that has been converted into the yellow. They have presented these results. Similarly, they have pesticide inhibited, and they have the different options. But the red one that has been highlighted, this is the main mechanism, and the other are can be considered as a control 1, control 2, control 3, or control 4 for the different options. So these are the students they have worked for this one. We have fabricated the paper-based sensor. This paper strips has been fabricated by the students, and these are very simple to fabricate. They have used the ordinary filter paper, and they cut it into the smaller sizes, into the smaller strips, and then they combine the two strips with the help of the double-sided tapes with each other, and then they pinches the holes in it to make the small well, or you can say this is the enzyme zones, or this can be the testing zone. We can name anything about this one. First of all, they added enzyme and the silicon content dots in every well, and after that they added the pesticide in this one. So where the first one, where this you can see, this is in the B, pesticide capture. You can see the first one, this is a control, where this is the quantum dots are showing the green color. And when we added the pesticide capture pesticides in this one, then the color has been changed to the yellow. And then we can simply read this strip under the UV light with the help of the mobile, and we can analyze the result with the imagery, or we can analyze the result by the RGB calculations. So this is very simplest method for these detections. And the most important thing is that every pesticides have a different mechanism of interaction with the base material for the enzyme and the silica content. So overall, from the preparation of the well, and then inserting of the material enzymes and the silica quantum dots to the capture of the materials and then detection, this take total 8 minutes. And so you can done the complete analysis for this one. So I am here presenting some of the printing and fabrication of the papers. Our student has fabricated this one. The upper picture, this is showing the stenciling, simply stenciling, because we don't have any of the printing technique, very advanced techniques. So we uses the wax printing, and the inkjet printings with this one. And so this is a simple wax printing. The student had stencils different patterns over the filter paper, and they have wax printing manually over this one. Very carefully, and then heating small amounts so it can be spread evenly, and then it is dried, and then the channels are produced that are called the hydrophilic channels and the hydrophobic channels. And here we have the two options. We can use these papers or these sites as such for the investigation of the optical sensors, as well as we can use or we can design sensors, electrochemical sensors for this one. And the last one, this is analytical zone fabrication, where you can see the 3 electrode system has been integrated over the paper, over the spaces. 3 electrode system, that is the auxiliary, this one, and this has been done by the simple ink material. And the lower one, these are the different strips that has student has prepared, and these are the blank strips that has been proposed. Wax printed circular analytical zone for the preparation, and you can see the different holes, and in these holes they have do the experiments for the detection of this one, and they have inserted this material. So this is very simplest method. And validity of the sensor for the proposed assay is very important. So we have did the many replicated experiment as well, and we have compared this one, the traditional assay of the pesticide detection with the enzymes. In the traditional assays, they have uses some coloring agent, but we have uses the silicon quantum dots as a coloring article, that is of optical sensor for this one, for the detection of this one. And we have seen that silica quantum dots act as in nanoenzymes and exclusively possesses the upper oxidase-like activity without oxidase-like characteristics, freeing the corresponding assay system from the oxygen interference. Moreover, silica quantum dots as nanoenzymes are the green color, thereby imparting good fluorescence intensity and color change under the UV lamp in the nanoenzyme-based assays. So we have just this one, we alternatively produce this one. So these are the some of mechanism for this one. These are some of the results. I am presenting some of the interference results. You can see under the sunlight, one of the organophosphate pesticide, this is a chloropyrifos that has been used, and this has been integrated with different interfering substances. And with each interfering substances, every spot or every test zone has a different color, and so we can identify with the concentration as well as color indications. And melathionine, this has the different combination and the results. Similarly, we have dimethoate and parathion results for the same analysis. And for the ascorbic acid, hydrogen peroxide, boric acid, glutathione, nickel oxide, cobalt nitrate, oxalic acid, I'm presenting some of those results. You can see under the sunlight as well under the UV light. These are some of the results for the diazonium ions, pentathiones. These are also the organopesticides. This one is the second example for the environmental analysis, in which we have studies the pesticides into the wastewater. And for the sensors development, optical sensor development, this is one of the example with the cheapest material, that is the paper, and the cheapest technology, that is only the fabrication by the wax or something. And third example that I will discuss, this is the electrochemical sensor for the biomolecules. These are also called the chemical sensor unless they have been using some of the biological moiety, for example, enzymes, antibodies, or something else. Biosensor produces an output electrical which is proportional to the concentration of the biological analyte. This is the simplest. Everyone knows this one. That is, there should be the analyte, biological detection agent, and there should be the transducers, and that kind of signal conditioning. And this is the typical biosensors assembly for this one. So these are some of the biosensors we can use everyday life. These are the electrochemical sensor, optical, piezoelectric, thermal electric. You can see this is the pulse oximeter. This everybody knows about this one today due to COVID pandemic. And this is a glucometer for the glucose detection. This is the next one is the neurochemical sensor for the dopamine, nitric oxide, and then this is the pregnancy test for the detecting of the SCG protein in the urine, and then this is the pacemaker for the heartbeat and for the implanted rectical probes. These are the different example for this one. We can see in the biomedical sensors. So this is a microbe that is working over this one, and we have constructed, this is also the published paper. So we have constructed this screen printed electrode ourselves in the lab. In this, we have used a simple glass sheet, and we have mounted a 3 electrode system over it, and then has been mounted with electrical connection with the electrochemical workstation, or that is a potentiostat that is available into the lab. And this one is the fabrication of the sensor, how they have fabricated. 3 electrode was designed over the 3 mm thick glass slab, and the electrodes with the thickness of 0.5 mm were printed on the glass slab by using the diamond cutter. And in each carbon working electrode, the consistency of 0.5 centimeter length, 0.5 centimeter width, and 0.2 mm width. These are most important, that we have to define what is the area and what is the length, or what is the dimensions of the electrode. So you can calculate how much material has been utilized and how much material is used for the detection for this one. The area of silver chloride reference electrode is this one, and the area of carbon conducting auxiliary electrode, this has been like this one. And this electrode has the advantage, very most important advantage, that is you can wash simply with the water, and you can rinse it properly, and you can use another material and deposit over it, and you can use another material for another detection, for another analysis. This is the most important and very friendly for us, that we have used this lab for many experiments. We just wash this one, and we remove all the material, and we have put all the new material, and then we use another analysis. And so this is the mounted with electrical connections. This has been done by the students as well. They have to some of them have very good command over the electricity. So I'm very impressed by those students. Working electrode materials. This is the graphitic materials they have prepared, and they have mixture for this one. We have used this material as a working electrode material. This is the graphene oxide methoxy polymer that is coated by the silica nanoparticles, and this material has been deposited as a working electrode material. And we have used this sensor, or this is the screen printed sensor for the detection of the valine. These are the 3 important neurotransmitters into the body, biogenic neurotransmitters: valine, phenylalanine, and serine. We have used obtained these results, and very comprehensive. This is I have mentioned this one. This is the already published papers. So I'm just representing some of the material from there. So these are the results for this one, for the concentration optimizations. We have used also this one for the micro levels as well, and this for the same results. And this is for the interferences effect for this technique for this sensors. So this is overall 3 examples. We are working over the sensors for the detection of the energy, for the generation of the energy, for the detection of the analytes into the environmental samples. That can be related to many examples, and that are the sensors that has been developed for the detection of the biomolecules. So just these are the 3 examples. I hope so this can goes well. From this work, we have the third one, electrochemical sensors can easily be modified and reused after successful cleaning step of washing with the water and the acid. 3-amino acid has been screen printed over the carbon electrode, analyzed by the cyclic voltammetric technique and the other potentiometric technique as well. Electrochemical sensor shows a very distinct oxidation peaks, and each amino acid has been very respectfully has been detected for this one. So this is overall my presentation. So anyone have any questions? Thank you for this one. I all very acknowledge my university, Bahadur Zakir University, Multan. Even though for the limited resources, we are working some of the work, and the university has supported us many times and are supporting. And I am very thankful and acknowledge my mentors, and that is my supervisor, and who has from whom I have learned a lot, and my mentors in Pakistan as well, and my research students. They are asset for me, and they are very proud. I'm very proud of them. My research collaborators as well, and thank you. Long live Pakistan. Thanks.
Bismillahirrahmanirrahim. Assalamu alaikum and good morning, everyone. I am Dr. Muzammil Sattar, Senior Scientist at Nuclear Institute for Agriculture and Biology, Pakistan Atomic Energy Commission, NAAP, Faisalabad. Me and my group working on the IPM, integrated pest management and we contribute in environmental pollution, to reduce the environmental pollution by agriculture. And basically the pollution is nowadays a problem, not only in Pakistan, but throughout the world. We are facing different pollution problems in air, water, in soil. Addition or excessive addition of certain materials, pollutants onto the physical environment in air, water, and land, making it less or unfit for life or any human organism or living organism. So they create the pollution. And according to an American biologist, they define pollution as the undesirable change in the physical or chemical biological characteristics present in air, water, and land. They may or will harmfully affect human life. So the pollution is divided in two basic components: outdoor pollution and indoor pollution. Outdoor pollution, the pollution created by different pollutants, for example, smoke emitted from the industries and the chemicals emits in different factories, radioactive wastes, sewage of houses, which are semi-liquid or liquid or in the form of solid particles, discarded household articles, they all mixture decay from time to time and are the common pollutants. Solid waste management is nowadays a very important chapter or topic. And in Karachi, Pakistan, some NGOs are working on that. Basically, these pollutants classification of these pollutants are according to the form in which they persist. Primary pollutants and the secondary pollutants, they persist in the form in which they are added to environment are primary pollutants. For example, DDT and the plastic shoppers, plastic bags, these all are man-made. Whereas secondary pollutants are those which are formed by interaction among the primary pollutants, like interaction of nitrogen and oxides, oxides. And they are again divided in qualitative pollutants and quantitative. Those do not occur in the nature and as I said, man-made, and these are different types of pesticides, fungicides, and other herbicides. They pollute our environment And quantitative pollutants are those which are present in nature and become pollutant when their concentration reaches beyond a threshold level, like carbon dioxide, which is we all know important in the process of photosynthesis, but if they exceed, they create problems. According to their existence in nature, biodegradable and non-biodegradable pollutants. Waste products which are degradable by micro actions like sewage, and non-biodegradable are pollutants which are not decomposed by microbial actions. So these are very dangerous, like plastic bags, radioactive substances, and heavy metals. Natural pollutants in in water, algae is present, but when these nutrients increases, ultimately growth of algae multiplied. So sunlight do not cross the thickness of this layer, and they pollute the water. Anthropogenic pollutants, which are man-made and natural, like NOx and SOx, sulfur oxides and nitrogen oxides, and salts of heavy metals, radioactive wastes, and substances. Uncontrolled growth in human population increase the population demand, and to fulfill these demand, food increased. Our farmers try to enhance their production, and they spray different types of pesticides and fertilizers. So urbanization is also very such as industries and radioactive waste, strong winds, and they disturb all our climatic conditions. This slide shows the contribution of outdoor pollution sources, and this is I took this picture from Nature 2015 and shows the pollution level scales. Major types of pollutions are air, water, land, and soil pollution, and I add in this noise pollution also. The emission of any impurity into the air, such as smoke, dust, particles, fumes, odors, biological molecules, and radioactive substances, these are causing disease in human health and create problems. Climatic change, we all know climatic conditions change hoti ja rahi hain, or unseasonal rainfall. We face this, and nowadays we are facing this pandemic situation, and we face this by a very harmful situation. Major air pollutants are gases, sulfur oxides, nitrogen oxides, carbon monoxide, and carbon dioxide. Carbon monoxide produced by incomplete burning of carbon-based fuels, including petrol, diesel. Sources and effects of air pollution: emission from power stations, industrial process. They emit different types of solid waste, natural sources like volcanoes, forest fires. They present the petrol, diesel, and batteries. So they also affect the children's health. Whereas they affect on the nervous system and digestive systems and all health problems. Water pollution refers to the contamination of water bodies, addition of certain substances to the water, such as organic, biological, radiological heat, which degrades the quality of water. It's not only confined to surface water, but has also spread to groundwater. Sources of water pollution, runoff, pesticide, and fertilizers. Again, I said the application of indiscriminate use of different pesticides. 1/3 of all deaths in Pakistan is because of polluted water. And the effect on shortage of the summer season, climatic change, the climatic conditions. This pollution make a very disorderly conditions. This picture shows the land pollution. Soil is a thin layer of organic and inorganic materials that covers Earth's rocky surface. Any factor which deteriorates the quality, texture, and mineral content, or soil which disturbs the biological balance. Land pollution refers to the deposition of solid or liquid waste materials. Sources are domestic solid waste, garbage, and the effect on the soil erosion.
and create the loss of fertility. That's why farmers use different types of fertilizers. So noise pollution is also important. Noise is generally defined as unwanted sound effects like physically or physiologically and socially. Noise may be continuous or intermittent and may be of high frequency or low frequency. They affects the health and create problems like allergies, hearing loss, sleep loss, and high blood pressure, low level of sugar. And in the side of indoor pollution, you may face many problems from radioactive and sources, like we use cell phones and other computer and burners. They emit different types of gases and rays which are affect the human health. So human health is affected like stomach and pains and the heart failure, blood pressure. So in the role of agriculture, indiscriminate use of various pesticides and which is very harmful, and ये सिर्फ ना सिर्फ हमारे एटमॉस्फेयर को पोल्यूट करता है, बल्कि ये बहुत ज़र मुबादला भी इस पे खर्च होता है, और very expensive these pesticides, and create residual effect in the insects. Improper management strategies like हमारे farmers जो हैं वो अर्ली सोइंग कर देते हैं या लेट सोइंग कर देते हैं, उससे इंसेक्ट का थ्रेशोल्ड लेवल जो है वो क्रॉस कर लेता है और काफी प्रॉब्लम्स आते हैं, जिसकी वजह से पेस्टिसाइड फार्मर अप्लाई पेस्टिसाइड्स एंड दे डिड नॉट गो थ्रू द बायोलॉजिकल कंट्रोल्स, सो दे डायरेक्ट अफेक्ट द पब्लिक हेल्थ. व्हेन आवर फार्मर स्प्रे इन द मॉर्निंग एंड मॉर्निंग टाइम जब वो स्प्रे करता है तो वो शाम तक वेजिटेबल्स को मार्केट में ले आता है, जिससे काफी सारा उसका जो है वो रेजिडुअल इफेक्ट उसमें रह जाता है, जिससे हमारे हेल्थ को अफेक्ट होता है. So there is need to legislation and implementation and the lack of information about these harmfulness of pesticides. Environmental complaints, अब जैसे कि मैंने इसमें बताया कि इसमें noise भी है, इसका भी है इसमें contribution, solid waste है, odor है, waste water है, air है, and others. They play a role into the to pollute our environment. Solutions इस पे हम अगर बात करते हैं तो इक्विपमेंट मेंटेनेंस की जरूरत है फॉर प्रॉपर फिल्ट्रेशन यूनिट्स. जो धुआं इमिट होता है चिमनी से, उसको हम जो है वो फिल्टर्स लगा सकते हैं, प्यूरिफाई कर सकते हैं. वाटर पॉइंट सोर्सेज, नॉन पॉइंट सोर्सेज को हम चेक कर सकते हैं. एक्शन ऑफ म्युनिसिपल फॉर ग्राउंड वाटर एज वेल एज सरफेस वाटर. लैंड एप्लीकेशन में जो है वो इवन दो वी यूज आवर फार्मर्स यूज डिफरेंट टाइप्स ऑफ फर्टिलाइजर्स, इसकी जगह पे इसको रिप्लेस किया जा सकता है फार्म यार्ड मैन्योर से टू रिड्यूस नंबर ऑफ स्प्रेज बाय रिप्लेसिंग बायोलॉजिकल कंट्रोल एजेंट्स लाइक प्रीडेटर्स, पैरासाइट्स एंड डिफरेंट टाइप्स ऑफ पैथोजेंस. This is the my group is working on different biological control agents and a little contribution to reduce the pollution in the atmosphere. नॉइज लेजिस्लेशन, नॉइज में इसको कंट्रोल किया जा सकता है. हमारे मुल्क में कानून बहुत अच्छे हैं, लेकिन इट्स नीड टाइम ऑफ द नीड टू इम्प्लीमेंट these legislations and this quarantine to suppress the pressure horns, heavy headlights. So this light show, we need everyone's help to stop the pollution. First of all, we focus on ourselves. हम खुद सही होंगे तो हम किसी दूसरे की हेल्प कर सकेंगे. To keep yourself healthy, and it's your world and you make it clean. Thank you. Any questions? You're talking?
इसकी वो लगनी पड़ेगी Sliders of yeah.
Yes, sir.
नहीं ये तो आप स्क्रीन पे आ गया मेरे से आवाज आ रही है वहां से हाँ लेकिन मेरे से आवाज आ रही है इतना सा है Okay. Bismillahirrahmanirrahim. Good afternoon, everyone. And in the beginning, I would like to say my sincere regard and special thanks to Dr. Mulka for the very kind invitation. It was a little bit haphazard, let's say yesterday, but still I managed, and thank you very much again. You arranged my stay also. I'm a little bit, I know sometimes I do nakhra and all those things, but thank you very much again. Okay. So, and also, of course, you, your team, university, vice chancellor, everyone, I would like to congratulate you because I know it's a very bold step and very bravery of you, all of you, to arrange this conference in sort of COVID. We are still not COVID free, but I know in Punjab's cases are going down, but still it's challenging. So I congratulate you again for this. And also, I would like to say regards to Dr. Ashraf. It was very nice meeting to you also, Ashraf. So. Let's start. Actually, my research field is on nanomaterials, functional nanomaterials. We develop them, we characterize them, and of course, we are applying them for many, many applications. Actually, we are working on both kind of, let's say, functional nanomaterials. Still, I know it's a random word, but still so many materials, including molecules and inorganic materials, they can be, let's say, regarded under the umbrella of nanomaterials, because we are developing both molecules as well as inorganic materials. That's why I still use the same terms for both of them. Of course, molecules are much more smaller in size compared to still the conventional nanomaterials. As name suggested, of course, functional nanomaterials, let's say, lies within the umbrella where materials are developed for specialized applications. They can be ranged from one, you can see in this chart, the functional nanomaterials, their application can be from one or more of these, of course, beyond that also. But I choose this figure because most of this application we are still working in our labs. Like I said before, these functional materials can be inorganic, organic, and of course, in some cases, they are a mixture of both. Some you have layered by layered assembly, in which organic layer can be, let's say, followed by the inorganic or vice versa. So what we do actually after developing and characterization of these nanomaterials, we apply them for catalysis, different catalysis application, energy conversion, energy storage, electro-organic synthesis, electrochemical sensing, or even simple sensing, let's say, biomass conversion, in situ spectroscopy, and of course, some related application also. So these are just because I know it's more like physics platform, so I will not go into the details, but of course, we were developing many molecules from time to time for energy conversion application. Actually, in energy conversion, my main research field is water splitting. So we can split water, and then we can release oxygen and hydrogen. And hydrogen itself can be used as a clean fuel for the energy production, let's say. And yeah, so I will just skip this one organic part, and I will rely more on the inorganic. Okay, so this is all about the inorganic material we are developing for different applications. Okay, before let's say starting the materials, what kind of materials we are using, it's very important to know about how to make those materials, because a part of my research was also focused on synthesis of these nanomaterials. So we have developed in many cases our own recipes, let's say, to make these nanomaterials. So we can have, let's say, electrodeposition way of making them, anodization, colloidal thin films, spray pyrolysis, the solid state synthesis or solid phase synthesis, molecular precursor, hydrothermal method is a conventional method, CVD, PVD based thin films, laser deposition also, or laser assisted deposition, let's say, and then ALD also. The number 9 and number 10, actually, I did not perform them myself, but we were collaborating with different people in different parts of the world who were, let's say, sending these films, thin films for us, and then we were applying them for different applications. But of course, most of my part, when I was, let's say, in charge of my research, or early my career, let's say, I worked from number 1 to number 7, part of number 8 also. And we, of course, have modified many methods, because it's depend on what kind of material you want to make. And in so many cases, let's say one recipe is not working, then you have to change the method to apply another one. Or in some cases, you have to modify the recipe a little bit, because sometimes potential is more there in using simple techniques. So you don't want to really go to a very sophisticated technique like CVD, laser, or ALD, or even more than that. So in the beginning, of course, I was much, let's say, part of my research was focused on changing these techniques. I have even a few patents only based on the recipes. We have modified them, and then we develop these nanomaterials based on our what kind of applications, or let's say surface morphology, or as a whole, the type of nanomaterial we want to have. Okay, and beyond that, of course, these, like I said before, we are developing more catalysts, but of course, part of the research will also focus on the solar energy based material. I focus more on the colored material because they absorb within the visible range. So we can have bismuth vanadate, hematite, tantalum nitride, tungsten trioxide also. Most of them, they absorb below 700 nanometer of the visible spectrum. Actually, in fact, between 450 to 650 nanometer in most of the cases. So again, this is like synthesis of different types plus their application. In most of cases, how we develop the, let's say, device, that we have the thin films. You can see in this figure, the yellow color, the thin film of the surface. In this case, it is representing, let's say, bismuth vanadate. And then on top of it, we can coat our nanomaterial, which is a catalyst. This catalyst can be inorganic as well as organic material. And then, of course, we apply this for what kind of application we want to have. I start with the electrodeposition method. It's a very simple conventional method. You need to have metal ions in the solution. And then, of course, as a function of electrode potential and pH, you can deposit the nanomaterials on the surface. Of course, you have to perform this, or to make, let's say, thin films or certain pattern of the film. You have to little bit, let's say, get your hand wet with this technique to know really what you want to have, and how thick or what kind of morphology you want to have. Like you say, you can see in these cases, we have this very thin film. The cracks are showing, actually, the surface in between the cracks are showing the substrate. So you can already see how thin this film and even this film is. And of course, the pattern, you can, like I said before, you can tune them by using pH, electrode potential, or even in some cases, current density also. And in anodization, it's a little bit different than the electrodeposition. In anodization, actually, there is no need to have the metal line. Yaar, zara volume kam karoge apna. Volume. Okay. In anodization, actually, there is no need to use the metal ions like we did in the electrodeposition. So, but of course, electrodeposition has, let's say, a little bit more limited application for the synthesis compared to electrodeposition. But at least in this case, we have few instances where we develop nanomaterials. Like in this case, you can see we simply use the clean etched copper, let's say, substrate or foil, which is just a metal. And then again, as a function of pH and potential, we electrochemically etch it. It is a controlled etching in which a few ions are coming out of the surface as a result of applied electrode potential, because you are corroding it. But again, because of the gradient of the pH, those ions cannot go into the very depth into the solution because of the pH gradient. And they like to deposit back again as a function of electrode potential or the electronic environment around the electrode. So they get deposited back on the same surface. So it's like a phenomenon of self-etching and redeposition back on the same surface and the same ion of the substrate film. So in this case, you can see we have this beautifully arranged copper oxide nanoleaves. We extend this film, extend this application to silver. So when we etch the silver, you can see electrochemically, anodize the silver, you can see we made this beautiful silver nanoflowers. Of course, we have extended later on this application to many other, like cobalt, nickel foil also. Even iron foil or iron, let's say, layer can be anodized by using this method. Colloidal thin film is a very simple method. Actually, it's a so straightforward way of making thin films. So again, all those, let's say, metal ions which are soluble in water, you can just tilt the pH by using a certain buffer solution. And then, of course, slowly increasing the pH or the buffer, let's say, combination with the ions, you can start making those colloidal, let's say, dispersion in the medium. And then, of course, because we don't want to have a very thick colloids, because thicker colloids will make normally bigger particles. So we really made very fine, let's say, you can see almost these solutions look like clear, but actually they have those nanocolloids inside them. And then we just spray them or coat them on the surface, dry in the air. In some cases, we also anneal them. And then, of course, you can see we can have this thin films to a little bit thicker film, but still, let's say, thickness in terms of 1 to 5 micron, still we can control it by just handling. And of course, if you want to make thinner film, you can also do the spray coating or the spin coating also. Molecular precursor method. In molecular precursor method, we can use, there are actually many molecules which contain metal ions in metal, let's say, center in them. We call them molecular complexes. So they can also be a very good starting material to make nanomaterial. Like in this case, if we use this type of iridium complex, which is iridium trihydrate complex, again, as a function of electrode potential and electrolyte, we can oxidize it or anodize it or destroy it on the electrode surface. And then you can see in this case, we have this amorphous iridium oxide film, which is developed by using this precursor. Later on, by changing few parameters, we were able to develop this 1.7 nanometer size of the iridium oxide nanoparticle. And you can see it's highly crystalline compared to this one, which is totally amorphous. Spray pyrolysis. Spray pyrolysis is again a conventional method. You just heat the surface on which you want to spray, or you want to make the, let's say, thin film. And then you put the substrate. It can be iron, titanium, whatever it is. And then just by using a certain spraying, let's say, facility, you can spray or fine spray on the surface. And because the surface is already heated to 400 to 500 degrees Celsius, that falling spray shower very quickly anneal, and then you, in the end, you get the thin film of the material, whatever material you are using. And normally in this case, if your spray particle or sprinkle is very small in size, you can get 100 to 500 thick nanometer film also. And like you can see in these cases, we have developed different type. Actually, this is one of them is cobalt. They are not labeled. One of them is cobalt oxide, and one is nickel oxide, and one is copper oxide. But of course, we have iron oxide also. And in some cases, we have even prepared the photoreceptor film also by using this spray pyrolysis technique. Then hydrothermal method. Hydrothermal method, actually, I never worked during my PhD or even postdoc, but recently we have collaboration with few groups inside even Pakistan also. They were working on them. So as a, let's say, collaborative research, we asked them to prepare these type of materials, because they were more, let's say, used to with this hydrothermal method. So we, let's say, it's like a recommendation that we need to develop this film by using hydrothermal method. Of course, in some cases, they were not easy. Let's say it was not easy to develop these materials by using other methods. So let's say, in a way, it's an application of new method in our case, plus of course the advent of new materials for application what we want to have. So in this case, you can see this is the zinc telluride nanocube type. Actually, nano, I don't know what to call it, nano triangle or whatever it is, nano boxes you can call it, because what size of one box is around 150 to 200 nanometer. Then, okay, another application we have is of chemical vapor deposition. Actually, this work was done very recently when I was in Saudi Arabia. So we have developed this palladium-based thin films, which was developed by chemical vapor deposition. Palladium, in our case, for water splitting, was a very bad catalyst. And of course, I have tried it many times in past, and all the time, most of the time, I was failed. But the film which was developed by this method, you can see how porous in terms of morphology it is. And then we applied, of course, and you can see also, of course, this is like extension of, actually, this is a wrong film. So we actually extend this chemical vapor deposition method to further develop after palladium, let's say, example. We then apply the same technique inside Pakistan to develop nickel oxide, cobalt oxide, copper oxide, and iron oxide nanomaterial. This paper just appeared a few months back in this journal. And of course, it was part of that work, which was a success example for the chemical vapor deposition method. Then little bit about the characterization, how to characterize these nanomaterials. Normally, I mean, of course, you can start in different way, but in general, we can start with the surface examination on a micro or nanoscopic level. So you can start with the SEM analysis, scanning electron microscope. You can then have XRD to know the physical phase or the crystal structure of the material if you want to know the details. And then EDS is actually bulk analysis technique, elemental analysis technique, energy dispersive X-ray spectroscopy. It is actually an aiding technique with the SEM instruments. Normally, EDS is present or you can have it inside the chamber of the SAM. So EDS can give you a rough, let's say, estimation of the elemental composition in the bulk of your material. Then for more precise analysis, you can have XPS. Normally, XPS give you surface elemental composition on a very, let's say, minute level, usually 20 to 30 angstrom. Then you can extend this, let's say, characterization using Raman in some cases, of course, FTA also. Then BET and nitrogen absorption is more like for the porosity and the surface area. And normally these type of instrumentation, we need to have it to, let's say, sort of fully characterize the nanomaterial, whatever you are making. I will go through quickly because there is no time for that. SEM and TEM, of course, like I said before, you can use for the surface examination, how your material is looking in terms of on like microscopic or nanoscopic level. And yeah, you can see in this case, of course, if you want to go down below 50 nanometer, normally you need to use the TEM modification. But of course, like I said, SEM and TEM, of course, besides the imaging, they have so many other functions also. And especially from TEM, you can do so many other surface analysis on a small scale if you want to have from your materials. You can see also these are the TEM images. Then XRD, like I said before, XRD is more about if you want to know what is the crystalline phase present in your material. Normally, the nanomaterial we made, they are polycrystalline, so they contain more than one phases. But of course, you can also apply this technique to make even single phase material, single crystal material, let's say. And then, of course, XRD preliminary tells you about the phase of the material. Also, whether the phase pure material, you have different phases of the same material in it, or sometimes it's a mixture. Like you can see in this case, calcium carbonate, if you anneal it or heat it, you can have the release of calcium oxide. And you can see in the beginning, the peak is very small, but with the passage of time, the intensity is increasing. So this is how you can apply XRD to evaluate what kind of process. But of course, it has extended application. You can use on many inorganic material. Almost all inorganic material can be characterized for these two parameters using X-ray diffraction technique. EDS, like I said before, EDS is an aiding technique within the instrument of SEM. So it is more like a bulk technique for the elemental analysis. It gives you a rough estimation. Let's say you are developing one or two combination of two materials, and you really need to know whether the combination has produced that material. You can quickly do EDS, which take less than 5 minutes normally, and it gives you very quickly a rough estimation of what kind of elemental nature of your material. Plus, of course, extended application is elemental mapping. You can also do it. So let's say this is the material you want to do the elemental mapping. So let's say your material contains three elements. In this case, you can see it has sulfur content, nitrogen, and carbon in it. And you want to know the distribution of these elements in your material. So you can, of course, do the elemental mapping. Then it will show you where each element has been distributed over the what kind of nanomaterial you have. You can see in this case, you see more red. It means sulfur is more distributed almost everywhere in this material. You can see more or less same with the nitrogen. Plus carbon, you can see carbon is more towards the extended strands of this nanomaterial. Then we have XPS. XPS is actually, in terms of elemental composition, is known as mother of the inorganic electric characteristic technique for nanomaterials. XPS gives you a very precise control over the different type of element you have, their oxidation state also, and sometimes it also tells you whether the element is present in a free state, or sometimes the element is in combined state, let's say with oxygen, normally in carbon, but it's not a chemical bonding. So XPS even tell you whether the oxygen is present in a free state or in a combined state, which is actually very difficult to know by EDS analysis. So it's a very, let's say, highly precise technique. So I will now quickly jump towards the applications. So I showed you different materials we are developing by different techniques. And of course, primarily, most of this material, we apply them for electrochemical water spreading. But of course, we are extending these applications to CO2 reduction and conversion, light harvesting, just like solar cells, electro-organic conversion, electrochemical sensing, biomass conversion, in situ spectro-electrochemistry. So I will just give you at least one example from each. I will just skip this one. Okay, I will also skip this one for the molecules. Okay, so this is example of electrode deposition. I told you in the beginning that we are developing almost all the first order transition element in their pure form and also in the combined form like binary oxide or ternary oxide. We can now easily develop by electrode deposition. In this technique, because I told you that we have patented it actually, we got the patent out of it. We have developed a new way. So what is the new way is we can use the carbonate, let's say buffer solution, and then we can purge CO to form the carbonate buffer solution. By purging the CO2 make a complex with these metal ions like nickel, cobalt, or iron, and then the solubility become, let's say, increasingly easy in these solutions. And then it becomes so easy because the pH is very close to 7. It becomes so easy to have the controlled deposition of these films. In anodization, I already gave the example, and you can see also with respect to catalysis, the copper oxide, the how to say the efficiency in terms of like what potential it is started to produce oxygen evolution current for water splitting. So you can see around 1.6, 1.7 volt, we have the oxygen evolution going on for copper oxide nanofilms. And of course, if you compare it with simple copper, the current density, the electrode potential will be close to 2 volt. So this is like the advantage of having this conversion of copper into copper oxide and also the in nano, let's say nanomorphology. In spray pyrolysis, we have developed this nickel oxide, cobalt oxide, and copper oxide nanoscale films. And you can see this is the difference. So when you have this catalyst on the surface and when the surface is without the catalyst. So you can see in all cases, there's a huge difference in terms of at what potential the current started to rise for water oxidation. Okay, next one is, maybe I skip one, this one. Yeah, this one is for the colloidal method. So you can see also after having the colloids, and of course we do few surface treatment also. So you can see in each case, the black one is the blank electrode where there is no catalyst on the top of the surface. So you can see in all cases, the current density is increasing, not only increasing, but of course the potential is also shifting towards the negative side, which means that with the presence of these films, the whole system become active for water oxidation, electrochemical water oxidation. In solid phases, actually, it's a simple way. So you can have 1 or 2 metal oxides, and you just blend them in solid phase, and then just annihilate to have those molecular bonding or ionic bonding, metal bonding, let's say, in between them. In this case, you can see we have different type of metal ferrite. Actually, we were working on magnetic material, but later on, I asked my student that can we have, or maybe there's some way we can convert this system into a water oxidation catalyst. So you can see these material. Actually, there is no comparison is shown in this figure, but still you can see this cobalt ferrite is active compared to the bare electrode for water oxidation. Molecular precursor, I told you already method. So you can see in terms of efficiency, around 1.4 volt, this material is able to do water oxidation, and of course at very high current density also. Molecular nanocrystal. Actually, this is a new emerging area in nanomaterials or functional nanomaterials. Actually, in fact, these are molecules, but inside they contain metallic cores. So it's very difficult to define them whether they are molecules or nanomaterials. That's why people have used the terms molecular nanocrystals for these type of material, because they have a molecule in the vicinity, in the periphery, let's say, and there is a metallic core inside. And the beauty of these type of material is you can really pinpoint them with respect to how many atoms you want to have and how big size you want to grow. Like in this case, you can see this nickel based, let's say, nanocrystal. We have only 4 atoms in this entire, let's say, assembly. And the size is, of course, less than 1 nanometer even. It's in few angstroms. Same with this one. So in this case, we have only 4 nickel atoms. And in this one, we have only 6 nickel atoms. Of course, when you have the nickel ions in the solution and you reduce them to make nickel metal, by the application of these thiol type ligands, you can really stop the further growth of the nanocrystal. And then, of course, the growth is just stopped, and you can have this really controlled size. So you can see in this case, we have the conversion of these nickel 6 and nickel 4 into very efficient water spreading catalysts. Platinum thin film, I told you before, I tried many times for last 4 or 5 years, and I was all the time, I was not getting very good, or let's say very efficient films. But by this CVD method, especially having this surface morphology, which is very rough, and having very high surface area. Actually, this nano impression are very advantageous in terms of electron transport at material transport. This is one of the reasons, of course, we don't know the much details, but this might be one of the reasons why we have this, the efficiency is so high compared to simple palladium. And then we extended this application, like I showed before, for conventional metals like nickel, cobalt, iron, copper also. Then we have this hydrothermal methods. Actually, we developed 3 or 4 telluride-based materials, cobalt telluride, zinc telluride, and recently we have copper telluride also. So you can see in all these cases, this is the example of the zinc telluride. So you can see the current density is really very high. And of course, the onset potential is below 1.45 volt, which is, let's say, one of the best in these telluride-based materials, which were published before that time, because this paper just appeared 2 years back in JLC. I will skip this one. Actually, this solar-based film, also most of the film, we developed them by spray pyrolysis. I told you also, like this was vanadate, and hematite also we developed by spray pyrolysis. Hematite is iron oxide. I will skip this part. Okay, then another application is CO2 conversion or reduction. Actually, CO2 conversion is a very challenging research, but the beauty is that by tuning the electrode potential, you can see in each case, electrode potential is different. But of course, it's not only the electrode potential, but also the type or nature of the catalyst. So let's say by controlling the nature of the catalyst, pH or electrolyte and the potential, of course, you can have more than 1 million product out of CO2, simple CO2 conversion, let's say. So in this case, you can see already CO2 can be converted either having 1 electron transfer process, 2 electron or multi-electron transfer process into so many chemicals. You can make formic acid, you can make carbon monoxide, which can be combined with the hydrogen to make syngas. You can have formaldehyde, methanol, ethanol, even methane gas you can make. So this is, let's say, in a way, beauty of this CO2-based research. But of course, I said it's highly challenging, very difficult, and of course, there are so many things which still need to be understood. So in one example, we have developed this copper oxide, let's say nanohairs, on same copper surface by using heat treatment or annealing. And you can see once we apply it for the CO2 reduction, we can have not only increase in the current density, but in terms of product, let's say what kind of product and how much we are having it. You can see compared to simple copper, we have enhancement in the product selectivity and also in the current density. Plus, of course, the less electrode potential is required compared to simple copper. And it's actually a very straightforward material, straightforward way, let's say, of synthesis. You can just clean the copper foil, put it in the oven at put it in the furnace, and then by controlling the heating, you can have this. Later on, we combine these two. So to get, let's say in electrochemical cell, we have anode and cathode. So after having this CO2 reduction catalyst, so what we did actually, we combined these two systems together in just one assembly. So on the anodic side, you can see we have this water spreading catalyst, which is cobalt oxide, which we developed in our lab. And on the cathode reduction side, we have this one. We have this copper oxide nanohair type catalyst, which we also developed in our lab. The good thing about this water spreading catalyst, because it is developed in CO2, so it has very high stability. Normally, CO2 has an etching behavior. So it starts eating on the anodic side. But in this case, because this catalyst was stable, so we have no problem. So we can easily make oxygen on the one side of the cell. And of course, then proton travels toward the reduction side, where carbon dioxide can, let's say, combine with the proton and water to make different kind of products. And of course, you can then analyze them by having online gas chromatography. In this case, we have this electroless conversion of CO2. So we develop this combination of material, which you just put in the sunlight, and then of course, it's just like a powder. So you need to have a glass of water and purge with CO2 gas, and then just put this material and put it in the sunlight. As a, let's say, result of this photochemical process, CO2 can be converted into, in this case, of course, we have the conversion of CO2 into methane gas. But of course, the efficiency was not so high, but still it's a, let's say, it's a beginning or introductory example in which we show that the CO2 directly can be converted into methane gas by using these type of materials. Then, of course, we also apply this material for different dyes degradation. Biomass, actually, it's a very interesting project. You know, these plastic bottles we have, they are made up of PET plastic. The problem with the PET is non-biodegradable and non-recyclable. And also the ingredient of the PET are coming from the fossil fuel. You know, there's a terephthalic acid which is used in, let's say, it is actually blended with ethylene glycol to make this plastic. So in a way, it's a very dirty plastic. So people were for the last 5 to 10 years people were highly, let's say, recommending that we should go in general, not only for this plastic, but in general, we should go more towards the biomass. So we have identified 2 or 3 chemicals which can be used to make same type of plastic, not exactly, but same type, using the, let's say, bio-based or biomass derived material. Like in this case, you can say we can have this 2,5-furan dicarboxylic acid, which can be obtained from hydroxymethyl furfural. And furfural can be easily obtained by different type of biomass. Same for the ethylene glycol, you can have these sugar alcohols, which can be coming from the different type of glucose. And of course, glucose can come easily also from different lignin sources, which are present in the wood or in the biomass. Then this FDCA, this is furan dicarboxylic acid, and this sugar alcohol, sorbitol or xylitol, they can be easily reduced to ethylene glycol. And then these 2 chemicals can be condensed or blend together to make this new plastic, which is known as PEF. So this is PET and this is PEF. The beauty of the PEF is it's 100% natural. You can see why, because it's coming from the biomass. Then it's almost 100% biodegradable. So let's say if you take this new plastic and bury inside the soil, let's say in this university, after 6 months, 3 to 6 months, you will see more than 80% or 90% of the plastic become part of the soil. So there will be no more plastic left. And plus also another beauty is this plastic is almost 100% recyclable. So let's say you can recycle this plastic back and back many millions of times into the same plastic. So it's a very, let's say, actually when I was doing this research, or let's say I was part of this European consortium program in which 2 huge industries, including Coca-Cola, so they also put like $1 million in this research. But then of course, due to my other assignment, I have left Denmark and then I moved to another country for another project. But of course, this is a wonderful research project for physics people also, for chemical science people also, to start in Pakistan. In situ spectroelectrochemistry, actually, in situ spectroelectrochemistry, I was using it as aiding characterization for what kind of information I want to have. But then I discovered later on this technique can be an independent research project, especially for the young PhDs or things like that. So we can easily use in situ vibrational spectroscopy. It can be Raman, it can be FTIR. And I know in many cases, let's say universities in Pakistan, we have FTIR. In many labs also we have Raman spectroscopy. So we can easily inline this Raman or let's say laser spectroscopy, either FTIR or Raman, within the electrochemical assembly. And then at the same time, you can do let's say two processes. One is you can do on the surface by the application of electrode potential, whatever you want to have. And then of course, let's say if you just stay on one fixed potential and then you run the Raman scan, which take 1 to 2 minutes, you can not only, let's say, see what is going on the surface electrochemically, but you can also monitor in terms of its vibrational signal, what kind of changes you are making as a result of electrode potential. Actually, it's a wonderful way. And of course, it's not only that you need to have laser spectroscopy, but in general, many spectroscopic technique can be in line with your system to have two processes going on at the same time. That's why we call them in situ or online electrochemical spectroscopic technique. This is one of the example I conducted during my PhD, and of course, it was published later on a few years after. Electrochemical sensing, again, I entered into this field few years back, I think 2 years back only, because we were developing, I told you, we are developing so many materials, but we all the time we want to extend the applications. So few of, let's say, my colleagues and students, they were working on them, and I was thinking, why not to extend the application? So in the beginning, what we did, we have developed this nano gold surface in situ again. So simple, of course, simple gold. I don't have the figures, but I would have shown you. Simple gold surface is totally flat, and you can see this is almost on 5 micron scale, I guess. So it already have micro to nano scale impression on the surfaces. Of course, these types of impression shows that by simple, let's say, examination, that you have enhanced the surface feature. But of course, XRD shows us that we have not only enhanced the surface area, but also we have exposed more kind of certain phases or crystalline structures on the gold surface, which were, let's say, highly applicable, because then, let's say, out of nowhere, we apply this surface for arsenic sensing inside the water. So of course, these results were wonderful, and we were able to sense arsenic to 0.1 ppb level, which was very difficult to see. And other beauty is this surface is highly reproducible. You can use it more than 1 million times. Of course, we did not try it for 1 million times, but for 10,000 times we have used the same surface. It's very, in less than a minute, you can clean it, and then you can apply it again for the arsenic sensing. This paper also just appeared few years back. Then we extend that let's say application by using different materials. So now we are working, actually this work is almost done. We are just analyzing the data now. So we use the same platinum film which we developed previously 2 years back for water spreading. So we extend this application now for the sensing of lead, nickel, and mercury also, including arsenic also. And we already got very good results. So that was all about the research. And of course, whatever I have shown you, it's not like I'm a magician or like this. I need to have money all the time. So the data I've shown you, it's like about 8-9 years in the past, what work I have done. Of course, I'm doing so many things at present also. But of course, you cannot do active research without the money. You need the money and you need the infrastructure and facilitation also. So I was just lucky that I was having from time to time invitation, collaboration, my postdoc and everything in many parts of the world. And of course, most of the time people, those professors, universities, funding agencies, they will keep on giving me money and trusting on me. Of course, I want to say thanks to them. And also thanks to you for listening to me. Any question? And then I need 5 more minutes to tell you what crazy things I'm doing in Pakistan also. Question, I can see.
Actually, I want to know, I felt so interested when you were talking about the recyclable plastic. It's going on. So, but do you think, do you see any scope in Pakistan?
Of course.
Actually, we can see many things, but is there, currently, any project going on in Pakistan about?
From my side or in general?
From your side and in general as well.
Actually 2 years ago, 2 or 3 years ago, 2 years ago, let's say, because I finished with Denmark in 2017, end of 2017. Then in 18, of course, many times there were conferences. I was traveling back and forth from abroad. And I think in 2018, in somewhere, I don't know which conference, I first time showed these results because, before that, I was part of the project where industry was involved and they told me I cannot show this data or results to any, because still it's a highly specialized field. Not so many people are working on that. But the other thing is that all the, let's say, liquid packaging industries, like I told you that Coca-Cola is a huge brand now, and Coca-Cola put $1 million that time. And now a very huge company named Aventium, which is also based in Netherlands, it was also actually the most of the money of the project was driven by Aventium. Then European Union, in collaboration with Aventium, grant us the project. And because I was not, like, let's say, not my own project, I was part of that European project, which was happening in the fuel cell facility in Denmark Technical University. So I don't think so many people in the world are working on it. It's a highly specialized field. But of course, like I said, Pakistan, I don't think in Pakistan someone is really doing it except me. I started it, even, I started it with collaboration of 2 universities. But, very quickly, to be very honest, I want to be very honest. I came to know that people here mostly, they want to steal your idea or results and all those things. But in general, of course, I'm still open that if someone wants to have detail or collaboration or whatever, I'm still open to discuss all those things. And we can easily do it. And it's in these huge projects, it's not important that you only see that you can do the research, you can develop a product or formula, and whether you can apply here or not, because these processes are of global interest. So let's say you have some idea, some data, some conclusion, you can already share with those companies or industries, or even with the United Nations, because this plastic is also causing huge environmental problems. So you can directly, if you have some data, you can file a patent, and then you can go to the United Nations or a bigger platform and discuss with them, I have this, or at least I have this idea. And in many cases, they even give you money to pursue your ideas. Only thing is we are a little bit lazy, let's say, in some cases. But I know, if you ask me, there are so many, let's say, agencies or funding instruments in the world. Even if you want to pursue some specialization in Pakistan, they will give you money.
So definitely you can continue in Pakistan. Recently, NRP, actually that's very good platform.
NRPU is like, for the beginning, it's wonderful, of course, but in some cases you need a bigger money, and then you can't spend 2 years just to convince them. You got my point?
Somehow,
But still, it's wonderful. I know, Pakistan is not a very rich country. We have a lot of limitation of finance. I know it, but still, I really want to say, this is what I feel personally, that with let's say our legs or hands are squeezed, but still Pakistani government or HEC is still giving money from time to time. I think it's our responsibility now to do more productive research rather than just research sitting in our laptops. But you know, this project, this plastic is, of course, it's a
So exciting.
highly applicable here.
Actually, I made a survey of the biodegradable films for the packaging of the buses to very
Mhm.
I was interested in that. It was performed two functions, not only enhance the shelf life of the book, but also to sense the lifetime of the
Mhm.
material by any type of person, maybe the visual person. I was interested to involve some industry, but they were so much reluctant. They were not confident at the time that even they put money or they will receive or no. So they didn't show any interest.
Mhm.
Even after elaborating the details, they say, oh, it's really hard to wait for a long time to get the result. And we are just interested in some project. You put on it and after a few months you get the result and you're confirmed and we
You know what I feel? I work a little bit with the industry, let's say in terms of collaboration and discussion in Pakistan. And what I see is in the past, you know, actually whatever our industry is today with respect to its relation with the academics, it's result of our past mistakes which we have done. Let's say our elders have done. And what are those mistakes is in the past industry has given some money to the universities, but universities were not delivering them, to be very honest. That's why industry is a little bit hesitant. To know, if you trust me, industry is still willing to give you money. Industry want to have it, but industry is reluctant that they will give you 1 crore or 10 crore. And then industry is a little bit scared that we will not able to deliver. This is-
very much scared.
so we have to somehow, let's say, on a bigger platform, convince them. You know, you have in Multan, I also know in Faisalabad, we have this chamber of commerce in Lahore also, Islamabad also. We just have to, let's say, negotiate and renegotiate with them more and more time. And also, you know, in terms of teams, not in terms of individual person. Let's say, if you go individually, university, the industry will not be trusting you. But if you go in let's say in the form of a group, especially on a bigger platform, like if your chairman or vice chancellor is also accompanying you to talk with the university, with the industry, then industry is more willing to do that. But of course, we need input from our hierarchy also. I think HEC should also take some initiative. HEC has taken like this industry academia collaboration, but still the missing link, which I feel a bigger party has to do it, because HEC put most of the effort on the researcher. I know researcher can't have this, let's say, tackling way of how to induce or convince the industry, or we need to have a training also. But still, like I said, I was personally in discussion with caustic soda industry, because they do brine electrolysis, the electrolysis of brine water by helping this electrochemical way. And this is my electrode material is my specialized field. So I discussed with them, and to be honest, they are willing to
Yes, sir. Actually,
participate.
The problem is that when we contact them, if there is a technical person, if there is somebody who is involved in research, that person can understand. If there is a businessman to whom you are communicating, it's very difficult.
Yeah, but then we need a business training. This is, you know, let's say you have a
research.
research, you have a research idea. But the thing is, researchers, I mean, most of researchers, we are all researchers. We have the idea how to take this research into this results, not even product, but results. From product to market, we don't know. We need to learn that
That is a
also.
gap.
We need, so there should be someone who gives training how to take your product to the industry, to the market, let's say at least. We should know it. You know what people are doing? They are making few things secretly, hiding from the government, and then making some money or all those by tricks, which is also not good in a way, because in this way, person earn the money, and in terms of government, let's say taxes and all those things, somehow they avoid it, and then government get nothing. But the problem is people don't trust the government, because government, once you register, government will take tax from you. But on the other hand, they don't give you the full, let's say, support in terms of taking your product from lab or production to the market. But still, I feel little bit, you know, if you ask me personally, I still feel we are also a little bit lazy, to be very honest. We need to have some time. We need to spend some time to, you know, this is what I do. I currently, I'm let's say supervising, or let's say taking a lead of a project of electric vehicles. And I did not ask anyone to give me money, because I know I can handle it with my own money. And I also don't need the market, because I know once I develop this technology, everyone will be, let's say, willing to buy electric cars from me, especially if it's, let's say, cheap in terms of its price and all those things. So still, I feel there are so many things we can do. We just need to open a little bit. You know, if you are keep, or let's say, scaring yourself and thinking in a way, oh, nothing can be done, this system is bad, this is good, it gives you a pessimistic approach inside you. And what will happen? Let's say if you are a faculty member, you will come, you will teach, go back home, and then that's all. But you need to have positivity inside you. Okay, even if there's a fire everywhere, you still have to believe that I will not let the fire enter into my home. अच्छा, मैं आप छोटे से 1-2 मिनट के लिए, क्योंकि थोड़े लोग बैठे हैं, वैसे बता देता हूँ। मैं ना खुद से कुछ चीजें कर रहा हूँ पाकिस्तान में। मैंने भी एक इदारा बनाया, इंस्टीट्यूट न्यू होराइजन्स के नाम से। उसका पर्पस यही था सबसे बड़ा कि जैसे ये स्टूडेंट्स हैं ना सारे PhD MPhil के, they don't have any guidance. I know it very well. I was part of UET about for more than 10 years, and I know it. No one is there to guide them properly how to pursue their education career. तो मैं जब पाकिस्तान आया कुछ आप almost कहने एक year हो गया, almost less than a year, but something like that. I was thinking that, and I was having free time. एक तो मैंने काम किया, मैंने ना कंस्ट्रक्शन का काम शुरू किया, मुझे शौक था उसका, मेरे पास अपना घर था, तो उसको रीबिल्ड करना था। क्योंकि कोविड था, एवरीथिंग वाज स्टॉप, तो मेरे जैसा बंदा वेला नहीं बैठ सकता, तो आई स्टार्टेड इट। मैंने एक नया काम स्टार्ट किया है, नई लर्निंग की। अब मैं सोच रहा हूँ अपनी कंस्ट्रक्शन छोटी सी कंपनी बनाऊं। तो ये ऐसे होता है, आपके दिन में आइडिया आपने किया, इट बिकम अ सक्सेस, देन यू डोंट वांट टू स्टॉप इट। फिर इलेक्ट्रिक कार, क्योंकि वो पहले भी मैं करना चाह रहा था, मैंने आप लोगों को बताया, तो मैंने उसको रीस्टार्ट किया। तो अब क्योंकि मेरी वर्किंग उस पर बहुत ज्यादा है, पहले था वो इट वाज इन स्क्रैचेस, नाउ आई हैव ऑलमोस्ट कंप्लीट डिजाइन एंड एवरीथिंग। तो मैं ऐसा ऐसे लोगों को, जो लोग उसमें पार्टिसिपेट करना चाहते हैं, स्पेशली विद रिस्पेक्ट टू डिजाइन, आई नीड मैकेनिकल इंजीनियर। इलेक्ट्रॉनिक्स का पार्ट तकरीबन मैंने सारा कुछ वर्कआउट कर लिया, मेरा फील्ड तो वो नहीं है, बट आई थिंक फिर बैटरी और फ्यूल सेल, क्योंकि मेरा अपना ही फील्ड है, so I will also try that to extend the application to develop our own indigenous battery, especially lithium ion battery. पाकिस्तान में कोई भी नहीं बना रहा अभी तक, ठीक है? पाकिस्तान में कोई सिवाय लेड एसिड बैटरी के कोई रिचार्जेबल बैटरी नहीं बन गई। और ये फिजिक्स वाले जितने बैठे हैं, फिजिक्स या साइंस वाले, ये बहुत जबरदस्त फील्ड है लिथियम आयन बैटरी का। और ये मुझे मालूम है, मेरा ना कुछ फौज के लोगों से कॉन्टैक्ट है कि जो मिलिट्री है ना, वो काफी इस पे फोकस कर रही है कि हम लिथियम आयन बैटरी या स्टोरेजेबल हाई एनर्जी डेंसिटी स्टोरेजेबल डिवाइस पाकिस्तान में बनाए। नस्ट को वो काफी बूस्ट करें, क्योंकि नस्ट में 2-3 बड़े-बड़े ग्रुप हैं जो ये काम कर रहे हैं। तो डॉक्टर मलका बैठी है, वरना मैं कहता कि आप लोग ये भी, या आप लोग जैसे फैकल्टी वाले हैं, इस पे काम स्टार्ट करें। एग्जैक्टली कर रही है, बहुत ज्यादा कर रही है, तो आप लोग जरूर ये काम स्टार्ट करें। 15 से 20 साल में, अगर आप मेरे बात पे ट्रस्ट करें, 15 से 20 साल में तकरीबन पाकिस्तान का 50% प्लस we have to shift on electricity. मैंने ये नहीं कहा we will shift, मैंने कहा we have to shift. Why? हम सिग्नेटरी हैं यूनाइटेड नेशन के। यूनाइटेड नेशन ने अगर आज अनाउंस कर दिया ना नो मोर गैसोलीन कार, तो हमें करना पड़ेगा। हाँ, 2-3 साल, 50 साल ही आपको देगा। तो ये चीज याद रखें। मैं भी एक गाड़ी लेने का सोच रहा था, मैं इसलिए नहीं ले रहा, मुझे पता है मार्केट में इलेक्ट्रिक कार आने वाली है या आ चुकी है। अभी सिग्मा और यूनाइटेड कंपनी है, तो उन्होंने मिलकर एक गाड़ी लॉन्च किया हाइब्रिड कार पाकिस्तान के अंदर। उसके 3 मॉडल है, 19.5 लाख का, 20.5 लाख का, 21.5 लाख का। तो वो तकरीबन इंडिजिनस मेड गाड़ी है, लेकिन मुझे थोड़ा सा दुखी हुआ कि उन्होंने प्राइस बहुत हाई रखी है। मुझे हो सकता है टाइम लग जाए, 1-2 साल लग जाए, लेकिन जो भी मार्केट में उसको गाड़ी होगी ना इलेक्ट्रिक कार में, मैं इलेक्ट्रिक की बात कर रहा हूँ, अगर 15 लाख की होती है ना, तो होपफुली मुझे बहुत उम्मीद है मैं वो गाड़ी कम से कम 10 यानी 5 लाख का डिफरेंस होगा उसमें लॉन्च करूंगा। मैं हल्का सा हाइब्रिड पे भी काम कर रहा हूँ, हाइब्रिड भी इतनी डिफिकल्ट नहीं है। तो देखें, मैं मैकेनिकल इंजीनियर नहीं हूँ, ठीक है, लेकिन ये आपकी एज अ रिसर्चर आपकी जो ट्रेनिंग हो जाती है ना रिसर्चर में, मैं एग्जांपल देता हूँ छोटी सी। फर्स्ट करें, मैंने ये बटन लगे हुए हैं, मैंने लगाए हैं। तो जब मैं बटन लगाना सीखूंगा ना, मैंने ठीक है शर्ट पे लगाना सीखे, लेकिन क्या मैं वो बटन सीखने के बाद पर्दों पे नहीं लगा सकता? व्हाट माय पॉइंट? तो जो रिसर्च की ट्रेनिंग होती है ना, वो रिसर्च की ट्रेनिंग ये नहीं होती कि आपने उसी खूह में रहना जिस खूह में आप, समझ गए बात को? तो यू हैव टू एक्सपैंड दिस एप्लीकेशन। आपने अपने किचन में पराठा बनाया है, तो आप इतने बड़े तवे पे भी बड़ा पराठा बना सकते हैं। सिर्फ सोचना पड़ता है कि हाउ टू एक्सपैंड एंड एक्सटेंड दिस एप्लीकेशन। जो रिसर्च है वो लर्निंग है, रिसर्च नॉलेज का नाम नहीं है कि आप कहते हो कि नहीं मैंने सीख लिया, बस विद ट्रेनिंग है आपकी। मैं इसको ना आसान मिसाल में आपको समझाता हूँ। जिन लोगों ने गाड़ी चलाना सीखी हुई है ना, उनको पता होगा शुरू में आपने 800 सीसी या 600 सीसी सीखते हैं, 5-10 साल बाद आप 600 सीसी नहीं चला रहे हो। मैं अपनी बात करूं, मैंने 20-25 साल पहले, 20 साल पहले से सीखी गाड़ी चलाना, 15 साल पहले सीखी मैंने। मेरे अब्बू के पास एक पिकअप होती थी, मेरे अब्बू वाटर के डिपार्टमेंट में थे, गवर्नमेंट की थी, मैंने उस पर चलाना सीखी। तो मैं अब तो वो नहीं चलाता। अब हमारा रिसर्च में माइंड क्या होता है, हमने 10 साल पहले 800 सीसी चलाई थी, हम आज भी वही चला रहे हैं। ये सबसे बड़ा प्रॉब्लम है। हमें आज सोचना चाहिए F16 चलाने का, क्योंकि वो लर्निंग आपकी हो चुकी है, आपने एक्सपैंड करना है। तो हम लोग ये नहीं कर रहे। देखिए, हमें सबको ना अपना, मैं ये नहीं कहता हम गलतियां कर रहे हैं, लेकिन हमें छोटी छोटी मिस्टेक्स हम कर रहे हैं, स्पेशली फैकल्टी के लोग जिन्होंने इन यंग लोगों को मोटिवेट करना है, या क्या कहते हैं इंड्यूस करना है। तो हमें थोड़ा सा ना खुद भी रिस्पॉन्सिबिलिटी लेनी पड़ेगी। वो पीएचडी की एक फीमेल थी, पता नहीं वो अंदर कह रही थी ना मेरे हस्बैंड भी है, बच्चे भी हैं, ये भी है, वो भी है, तो फिर छोड़ दो काम। मैं इस तरह का बंदा हूँ, तो मैं इतना स्ट्रेट फॉरवर्ड इस मामले में कि मैं कहूँगा छोड़ दो फिर। तो कोई देखें, जब आप जॉब कर रहे हो ना एंड यू आर टेकिंग मनी, आप रिवार्ड ले रहे हो, तो आप एहसान नहीं करेंगे, आप घर बैठ कर ना करो, करना है तो फिर सही काम करो। तो ये एक्सक्यूजेज होते हैं। रिसर्च पे अगर आपकी फैमिली भी है और जॉब भी कर रहे हो, तो आपको अच्छी तरह पता है आपकी जॉब 8 घंटे की है, तो यू हैव टू वर्क 8 आवर टू हलाल योर मनी आल्सो। ये सिर्फ हलाल वाली बात भी नहीं है, हमें पता है पाकिस्तान की रिसर्च, टेक्नोलॉजी, साइंस, एजुकेशन नहीं इतनी अच्छी, तो हमें रिस्पॉन्सिबिलिटी लेनी पड़ेगी। हम कहते रहेंगे गवर्नमेंट गवर्नमेंट गवर्नमेंट, गवर्नमेंट का कसूर नहीं है इतना, हम सारे सब ने मिलकर इसको करना है। और फिर दूसरा असूल क्या होता है, अगर लेट्स से आपकी ये थिंकिंग है जो मेरी है, आप कहते हैं सर यहाँ पे कोई सपोर्ट नहीं कर रहा, मैं कहूँगा टेक योर ओन इनिशिएटिव, डोंट लिसन टू द पीपल। अच्छा, मैं बता रहा था स्टूडेंट के रेफरेंस से, तो मेरे दिन में ये चीजें चल रही थी। मैंने ना 2 साल 1 डेढ़ साल पहले यहाँ पे आकर ट्रेनिंग भी करवाई थी, जिसमें मुझे याद है सितंबर या अक्टूबर की बात है, कोविड से पहले की। तो मैंने उसको बताया था अपनी टॉक में कि मैं एक इदारा बनाने का सोच रहा हूँ ट्रेनिंग का, जहाँ पे रिसर्च की ट्रेनिंग दी जाए। और मैंने ना पिछले 2 साल में तकरीबन कोई 40 जगहों पे ना पाकिस्तान में ट्रेनिंग दी है, तकरीबन सारे पाकिस्तान में, कराची से लेकर कश्मीर तक। फिर कोविड आ गया, चीजें थोड़ी सी स्लो हो गई। उसके दौरान फिर मुझे टाइम मिला, तो मैंने ना अपना खुद इदारा बनाया छोटा सा लाहौर में, इस ट्रेनिंग के ऊपर ये सारा। तो उसके अंदर से फिर मेरे होता है ना कि यू कीप ऑन थिंकिंग एंड यू देन लेट्स से क्रिएट और इन्वेंट न्यू आइडियाज। तो मेरे पास नेक्स्ट आइडिया आया है और के जो लोग स्कॉलरशिप के लिए बाहर जाना चाह रहे हैं, उनके लिए मैं कोई ट्रेनिंग का प्रोग्राम करना शुरू करूँ। मैंने वो स्टार्ट किया। तो अब वो सिर्फ ये नहीं कि वो ट्रेनिंग है, वो बिल्कुल ऐसे जैसे आप किसी इदारे में जाते हैं, एडमिशन लेते हैं, फी पे करते हैं, तो फिर वो इदारा आपको 2 3 4 माह प्रिपेयर करता है, ट्रेन करता है, ना सिर्फ ये करता है, हम तो अप्लाई भी करते हैं। मैंने वो भी लॉन्च कर दिया है। अभी नेक्स्ट मेरा प्लान है जो है रिसर्च फाउंडेशन बनाने का लाहौर में। होपफुली आई विल स्टार्ट विद दैट। इलेक्ट्रिक कार प्रोजेक्ट मैंने आपको ऑलरेडी बता दिया है, तो मैंने यहाँ पे रुकना नहीं है। तो ये हो जी चीजें। फिर 1 2 और प्लान है जो मेरे माइंड में ऑलरेडी चल रहे हैं। फिर एक जो है रिसर्च फाउंडेशन के साथ मैं एक छोटी सी रिसर्च लैब भी बना रहा हूँ, तो वो ज्यादा वही होगी जो मेरे एरिया में है, लेकिन ऑफ कोर्स एक बार वो एस्टेब्लिश हो जाती है चीजें, तो फिर मैं उसको एक्सटेंड भी कर सकता हूँ। और मैं इसलिए सारी चीजें कर रहा हूँ या करना चाह रहा हूँ कि उस एक्सक्यूज से हम लोग बाहर निकले कि फलाना गवर्नमेंट नहीं कर रही है, यूनिवर्सिटी नहीं कर रही है, वीसी नहीं मुझे करने दे रहा, चेयरमैन नहीं करने दे रहा। जो चीजें मैं घर में किचन में बैठ के कर सकता हूँ वो तो कर सकता हूँ। मैं आपको सच्ची बात बताऊं, जो स्प्रे प्रोसेस मैं बता रहा था ना, अंदर भी इधर भी, मैंने ये चीजें ना, मैं उस वक्त यूईटी में था, वो जो हीटर नहीं होते, वो जो बिजली के हीटर होते हैं, उस पे बनाई थी खुद अपने हाथ से। इट कॉस्ट लेस देन 50,000 रुपी, लेस देन 50,000। और आप अगर वो इंस्ट्रूमेंट खरीदते हैं ना, वो 40 40 50 लाख रुपए। इतनी चीजें हम लोग कर सकते हैं, हमें बहुत हल्का सा ना, वो कहते हैं अपनी गरारियों को जो जुगाड़ लगा हुआ ना, वो करना पड़ेगा। फिर मैंने ना कुछ स्टूडेंट्स के लिए, जो यंग स्टूडेंट है ना, उनके लिए प्रोग्राम पे काम कर रहा हूँ। वो ये कि स्टूडेंट वो पूछ रहे हैं कि सर कोई ऐसा काम नहीं है पार्ट टाइम में हम जिससे अर्निंग कर सकते हैं। मैं उसमें भी थोड़ा सा काम कर रहा हूँ कि कुछ मैंने चीजें ऑलरेडी बना भी ली हैं, लेकिन अभी स्टिल आई एम वर्किंग ऑन इट। तो लेट्स से इन 2 3 मंथ्स इफ आई कम बैक हियर फॉर सम लेक्चर समथिंग, मैं आप लोगों को बताऊंगा वो क्या क्या चीजें। स्टूडेंट घर बैठ के 2 3 घंटे काम करके ना, दे कैन अर्न दैट मच मनी कि अपनी इनकी एजुकेशन कम से कम और शायद सेल्फ सस्टेन्ड हो जाए, किसी पे डिपेंडेंट ना रहे। और वो और जॉब भी नहीं होगी, रिस्पेक्टेबल जॉब है, दे कैन डू व्हाइल सिटिंग एट होम। इस तरह
तो दोनों गुजर गई है मैडम से कुछ नेक्स्ट टाइम।
वो भी इसीलिए है कि लोगों को नजर आए कि यार कुछ किया भी जा सकता है स्वाइल में बैठे। मैंने कोविड के दौरान इतना कुछ किया, मैं भी तो उस कंस्ट्रेंट में था। थैंक यू वेरी मच सर। क्वेश्चन तो नहीं था किसी का?
जी यस सर अली, क्या मैं स्टार्ट करूं?
जी स्टार्ट करें।
अच्छा ओके, थैंक यू। आपको मेरी आवाज आ रही है?
जी आपकी आवाज आ रही।
अच्छा, okay, thank you. Assalamu alaikum and good afternoon to all of you in this event. And although after some delay we are starting, but it is good to start at least. Okay, I will be presenting on enhancement of solar cell efficiency by luminescent downshifting by an optimized cover glass. Now in this talk, I will explain you that how we can enhance the solar cell efficiency by utilizing some specific phenomenon and without changing the composition of a solar cell. So this is interesting in this way. What we will discuss today, we will discuss what is our problem. Our problem is we want to increase the efficiency of our solar panel. And then we will resolve this problem. Then there is a method how to resolve this issue. And then we will have to check that whether we have resolved the problem or not. And we know is the earlier speaker Khurram told us that being a researcher, we are having the results, not the product. So we will have to check our results that whether we have resolved the problem in real-time measurements, because one are the result that we get from the instrument, and the other are the result which we get in our real time. For example, our device is giving some result like solar simulator is a device and it is giving some result about our efficiency, for example. Then weather, sun is also giving the same efficiency and that is the real time. And the fifth, we will discuss the side effects which are caused during the resolution of this issue. So we will, as we are treating the glass, so we will check our glass whether we have compromised some of the parameters of this glass or the glass is the same. And then I will conclude my talk. So let's start with the introduction. And the introduction, the introduction is that we know that from the solar spectrum, we are having a broad range. This range includes some X-rays, very rare portion, but there are X-rays, and the UV, the ultraviolet, we are having the visible, and a big spectrum of the infrared. So our solar cell is actually optimized for the visible range only. And the UV portion is degrading our solar cell, while the IR portion, which is a big portion, is heating up our solar cell. And due to these two, we are having a decrease in the performance or in the efficiency of our solar cell. This one, for example, if I focus on the UV, then we know that some of the solar cell, for example, the very good solar cell like gallium arsenide, they are being degraded, and especially the perovskite solar cell are degraded much in UV. And in IR, we are having the problem of the heating up of our system, and which cause this one. I'm not focusing on the IR, but on the UV. If it is causing degradation of our solar cell, so we want to get rid of the UV in the spectrum. And not only to get rid of the UV in the spectrum, but also to convert this UV into visible in order to enhance our visible range here. So let's how we will do this problem, how we will resolve it. We will dope our glass with gold nanoparticles or any other transition metallized nanoparticles, and we will segregate them with the help of nanosecond laser. And I will tell you what's the need of segregation. As we know that light on any glass, it is 4% reflected. So we have already lost 4% of the incident light, and the available light with us is 96% is a home. Then when we will dope our cover glass, it will remain the glass, of course, so this 4% will be lost, and still we are having 96% available solar light. We will exploit the phenomenon of luminescent downshifting. Luminescence will occur inside the glass, and it will cause downshifting of the solar spectrum. What we will have to avoid here, that the glass shouldn't self-absorb, because we are already losing 4% of the light, and when the glass will start self-absorption, we will lose more light. And another thing, we cannot change the nature of the glass. So the considerable changes are not allowed, because our glass is supposed to be a glass itself. And for that, we will have to take care of the experimental parameters not to change the glass. So what will happen, that when our solar light will fall on our core glass, then it will absorb the UV and it will downshift the UV to the visible. And we will have more visible range here to our solar cell compared to the solar spectrum, which is directly falling on the solar cell. Now, how to resolve the problem? We dope the glass with the help of gold nanoparticles, and the technique that I'm using is the solid state ionic diffusion, and we will segregate the particles with the help of nanosecond laser. As I can see that this is the optical density and the absorption of the glass, and I don't see any surface plasmon resonance here. And the surface plasmon resonance, when it is absent, then it means that the self-absorption of the glass is not there. In common words, I can say that there is no glass coloration, because coloration is due to the surface plasmon resonance. As we are doping metallic nanoparticles, are diffusing metallic nanoparticles, so it causes, when their concentrations become more or their crystallization occur, then there will be self-absorption. Even though we don't have any self-absorption here, when there is self-absorption, we will have to avoid that glass. But even in this situation, we may have some faint absorption due to those metal nanoparticles, which is causing the self-absorption. So we will have to segregate them with nanosecond laser into dimers and trimers, and that way we can utilize the luminescent downshifting phenomenon. We can see if the FTIR that we have treated the pure soda lime glass at this temperature, and these are the electric fields that we have applied across the glass, and these are the irradiated, means the nanosecond irradiated glasses, and we can see that there are no considerable changes in the structure of the glass. So we want to maintain or keep the structure of the glass as it is. Now we will have to check that whether we have resolved the problem or it is not doing our job. So let's go directly to the photoluminescence of these samples. We are having the excitations, means I'm selecting two wavelengths in the UV range, which is 260 and 340. This is close to the start and this is close to the ending. When I do excite a 260 nanometer, then I see that the emission starts after 300 and it goes around 375 and it is going into the visible range. So what I did, my matrix absorbed the UV and I'm getting the emission in the visible range. If I do excite it at 340 nanometer, then I see that it is completely converting it into the visible range. And the proportions are also good here. This is the reference. And now we are having here the schedule, means I can see that here is 400 and 400. And when I do irradiate this one, then I can see that its emission into the visible range increases. Similarly, at 400 and 500, this one is the just doped glass, and this one is the nano laser treated glass. So this way we can do the 340 as well, and I can observe that a huge change occurs in the emission intensity. Now, this is not the efficiency, but we have increased the luminescence intensity here. Now, we will have to do some real-time measurements with a solar simulator. And here are, because the sample that we were treating were very small, like 0.5 centimeter into 1 centimeter. So we cannot directly do them in the sun. And for that purpose, we are having the solar simulator with us, and the sample sizes are 0.5 to 1 centimeter. And I can see here that this is the open circuit voltage, and this is the current, and here I'm having the power. And the results which were shown in the photoluminescence, these results are very much in accordance to that, and we are having a considerable increase in the efficiency of these samples. If I go to the part directly here, then I can see here that this is our reference, and now we are having the photodiode array, which we are using just below our cover glass. So this solar cell we have taken, this is BPW34, a standard, and on this we are having our cover glass, and we are just measuring it directly into the solar simulator. And then when we put our solar glass at 400 and 400, then I can see that it has increased. And to explain this more here, that why the reference is below this one, because as I told in the introduction of this talk, that 4% of the light, the glass is already reflecting. So when we are having the glass, then it is having, means the reference glass, it is having this much power. And when it is naked, just the photodiode array, then that 4% is utilized and the efficiency will definitely increase. And when above this photodiode, I put my other treated cover glass, then it has increased the efficiency of it. And similarly here, and here they are proportional. So this way we can utilize this innovative idea. Is we know that many people are working on the composition of a solar cell, and as I have shown you the different generations of solar cell, like from the dye synthesized solar cell, and we are having the silicon solar cell, we are having the gallium arsenide, and now trend is going toward the perovskite solar cell. So all that range or generations of solar cells, people are doing a lot of work on their composition. But here we are not changing the composition, but we are doing a simple method in order to enhance the efficiency of it. If we go to the composition of it, then there is, let's say, 1% or fraction of a percent change in the efficiency. While if we do utilize this innovative idea to optimize the cover glass, then approximately 3 to 4% change will occur in the efficiency. And those who are working in the solar cell or in field, then means the photovoltaics, they know that it's a very high efficiency to achieve. Now the side effects that although we have achieved some enhancement in the solar spectrum, are the output power that we have, but whether we have changed something, because this thing is supposed to be converted into a product, and for the product we will have to analyze all sides of it. So the glass, if we have changed the glass, not the structure of it, but changes have occurred inside the glass, and the very first thing that come into mind is the hardness of the glass. That whether we have changed the hardness of the glass due to this treatment, and for that we have done the Wicker hardness test with some specified loads in the dwell time, and here we can see that these are the diagonals of the indentations, and here we are having the average hardness. This is the reference glass hardness, which is 556. Our purpose was to at least maintain this hardness, but we can observe that with this treatment, the hardness has almost remained the same or increased in some cases. So the hardness of the glass has not been compromised, and this is a good news about our optimized cover glass. And now I will conclude my talk. It's a very brief one, and we will give more time to the question and answer. What we did, we doped gold nanoparticles into the soda lime glass at different experimental parameters. We irradiated them with a nanosecond laser in order to do the segregation of nanoclusters, means into dimers and trimers. These are the characterizations that we adopted. Like, we confirm that there is no self-absorption of the glass has no coloration. When this one is certified, then we go for any structural changes inside the glass, and that was also okay, the molecular structural changes which are occurring in the glass. Then with the help of PL, we made it sure that down conversion is occurring, or matrix is absorbing UV light and converting it into visible range. The nanosecond laser irradiation, the luminescent intensity was enhanced 50 times, and the PV performance showed an increase approximately 3.4%. The Wicker hardness test, this showed us that the glass strength remains the same or increase in some cases depending on the experimental parameters, and this innovative idea can be extended to other metal ions as well. At the moment, we have done with the silver as well, and we are working on the chromium as well. And we know that chromium exists in two oxidation states inside the glass, is chromium 3+ and 6+. 3+ is okay, but 6+ is very hazardous. So this way we can also make it safe. Inside the glass, chromium 6 remains safe, and that is another benefit of it. This talk was based on one of our article, which was published in Ceramic International 2020. One of my MPhil students did this, and let me acknowledge them. We are having some collaboration with the University of Padua in Italy and the University of Venice, and we extend our thanks to them. The financial support by the Higher Education Commission, one of the NRPU projects, and the Directorate of Science and Technology Khyber Pakhtunkhwa to one of its projects. And this is also to be noted that one of the collaboration is from Sargodha University. We did the nanosecond laser treatment from Sargodha University. Thank you for being with me. And now I am available for any questions or comments or discussion. So thank you.
Dr. Shah, thank you very much. Can you hear me?
Yes, yes.
Okay, thank you very much. It was a nice talk. I just wanted to ask you, in the conclusion section, you showed that the 4 or 5 parameters, and you were saying that there is an enhancement in almost each parameter, and then your overall efficiency is 3+% compared to what we have available. So the question is, can we apply this, let's say, new method or technology in terms of commercialization, let's say inside Pakistan at least?
Yes, of course we can, because as you know that this thing is working, and many people have tried this thing with different approaches. Some have deposited a layer, a downshifting layer on the solar cell, a transparent layer, and then they have put the glass. Now we are not doing any additional thing, but we are just changing the glass. So this thing is applicable, and now some of our results are coming up with efficiency measurement, as we have recently received our internal external quantum efficiency measurement. So this thing is supposed to be worked out more, but yes, we can do this for commercialization.
Thank you.
You're welcome.
Thank you, Shahid sir.
Okay, you're welcome.
सर आप आगे ना एक समाज करते हैं
Hello, everyone. Shall I start?
Yes, yes, please.
Good morning. So the next talk will be from Professor Coleman, and he's from Italy.
So, hello, everyone, and apologies for the change in scheduling. I think there was an issue with the time difference between Pakistan and the United Kingdom, where I am located at the University of St. Andrews. And so today I'd like to change topics and tell you about a new class of emitter materials for organic light emitting diodes called multi-resonant thermally activated delayed fluorescence. And of course, these are emitter materials that underpin the technology in organic light emitting diodes. This is a disruptive display and lighting technology that is rapidly taking over from the current widely used display technology, such as inorganic light emitting diodes and liquid crystalline displays. If one looks at the materials used in organic light emitting diodes, and in particular the materials responsible for the emission of light, there has been an evolution over the past 30 years in terms of the types of materials used for that evolution of, for that generation of light. Going back to the late 80s, the first types of materials which were used were fluorescent materials, and in organic light emitting diode, the way that excited states are generated in these molecules is by hole and electron recombination. And during that recombination, 25% of those recombinations can generate singlet excited states, and 75% can generate triplet excited states. Of course, in fluorescent materials, the 75% of triplet excited states or triplet excitons are lost as heat, and the only excitons that can radiatively decay and generate light are the singlet excitons. And so the maximum internal quantum efficiency of the device is really limited only to 25%. In other words, all of the singlet excitons generate light, the triplet excitons do not. And the first emissive molecule that was used in an OLED developed at Kodak Corporation is this compound here, known as ALQ3. It's an ice green emitter. So how to get over this efficiency barrier? Well, the solution came at the turn of the 21st century with the development of phosphorescent complexes. Due to the presence of a heavy atom in these metal complexes, this facilitates an intersystem crossing event. And so when you generate holes in electrons, the 25% of singlet excitons migrate over to the triplet manifold, they join the triplet brethren, and then you can get phosphorescence, that is emission, directly from the triplet excited state. And the typical types of compounds that are used are based on iridium complexes. I've shown you this example, a green emitting iridium complex. And quite wonderfully, the maximum internal quantum efficiency of these devices approaches unity. So this seems like a wonderful solution, except for the fact that iridium is the scarcest naturally occurring metal on the Earth's crust, and there's a limited supply of this. So in fact, large-scale rollout of the technology is going to be an issue due to the non-sustainable nature of these complexes. This has led to the development much more recently of so-called third-generation materials based on delayed fluorescence. In these types of materials, the energy gap between the singlet and triplet excited states is extremely small, and this allows for a thermally activated reverse intersystem crossing event where triplet excitons are upconverted to singlet excitons. And so in this type of material, what you tend to see is dual fluorescence. The singlet excitons rapidly decay via prompt fluorescence on a nanosecond time scale, and the triplet excitons, which are upconverted to singlets, decay radiatively via delayed fluorescence. So two emissions, both from the same state, but at dramatically different time intervals. The important thing is that the maximum internal quantum efficiency of these devices is likewise at 100%. And this is an extremely active area of research since the first high-performance OLEDs based on this class of materials appeared in 2012. You can see exponential growth in the number of publications that have arisen based on TADF emitters. How does one design a material to do this? Well, in more than 95% of all cases, they're based on a donor-acceptor paradigm, where the donor acceptor are very, very loosely electronically coupled together. And that's because the conformation between the donor and acceptor is highly twisted. And so here's an example from this compound DMAC-TRZ, and you can see that the donor electron density is located on the dimethylacridane. That's what's in blue here. The LUMO is localized on the triphenyltriazine. There's very little overlap between the red and the blue segments, and the degree of overlap correlates with the size of this all-important delta EST parameter. The smaller delta EST is, the more efficient the reverse intersystem crossing is, and the more and this will translate to a higher performing device. Everything you do to the design of thermally activated delayed fluorescence materials affects all of its properties. So the choices of donors and acceptors that are used affects not only the TADF efficiency as reflected in delta EST, but also the emission energy as reflected in the S1 energy state. The degree of electronic coupling makes a difference and can affect everything, but including how bright the emitter is, and that's linked to this oscillator strength F value that's here. The number of donors and acceptors that are used affects everything, and not only do we have to think about the lowest energy conformation, but also the degree of conformational flexibility, and that's because these movements, such as this rocking movement that you're seeing here, is responsible for something called spin vibronic coupling that also aids in this reverse intersystem crossing process. So if you can optimize all of these properties, you too can generate high performance organic light emitting diodes like these blue emitters that came out of my lab. Now, this looks like a wonderful solution, but there is an outstanding issue with this class of compounds, and that has to do with the fact that the nature of the emissive state in these TADF compounds is typically charge transfer in nature. And there's a certain degree of conformational flexibility that exists that leads to a relatively broad emission spectrum, and that leads to poor color purity. One of the ways to overcome that is to lock in your structure into a much more rigid type of conformation, and that leads to much smaller perturbations between the ground and the excited state in terms of that geometry, and a much narrower type of emission. And that is the basis for the development of multi-resonant thermally activated delayed fluorescence materials, which are based on P and N-doped nanographene fragments, as exemplified by this compound, commonly known as DOBNA. In this compound, where the electron density is in the HOMO and LUMO is offset by one atom. And that's schematically shown all the way on the left. It's probably easier to see these in these electron density distribution difference figures, where one can see that in blue, you see a decrease in electron density on going from the ground to the excited state. And in yellow, you see, or yellowy green, you can see an increase in that electron density. And so the fact that there is very little overlap between the blue and the yellow leads to a small delta EST in these compounds. But the fact that the compound is so rigid leads to a narrow emission. And that's really exemplified in the spectroscopic study that I'm showing here. So this compound is from a recently submitted paper of ours, which is a standard donor acceptor system that shows typical charge transfer emission. And you can see how dependent that emission is on the environment in which it's taken. So here is a solvatochromic study where we go from apolar cyclohexane to polar acetonitrile, and you see very strong stabilization of that excited state. And that's because you have a large redistribution of electron density on going from the ground to the excited state in these CT type compounds. Here's a compound I'll talk about a little bit more in detail later on, called mesdicta, and you can see that it too shows a certain degree of positive solvatochromism. In other words, we get redshifting in the emission as we go to stronger or more polar solvents. But that degree of redshifting is quite a bit attenuated, and that's because there's very little reorganization of the electron density, but just enough to get this small delta EST. Now, since the first multi-resonant TADF emitter was reported in 2016, there have been 57 of these emitters that have been used in OLEDs, and that may sound like a large number, but if you compare to the literally well over 1,000 separate donor acceptor systems that are there, this represents a very small part of the total chemical space of TADF emitters. So there are examples of now blue, green, and red multi-resonant TADF emitters. This is all very recent. There you can get very high efficiencies for blue, the most impressive of which is this compound by Hatakayama that was published a couple years ago with a maximum external quantum efficiency of about 34%. In the green, once again, you can see that efficiencies can peak at over 30% maximum external quantum efficiency. There are only 2 papers with compounds reported in the red. And this compound, like the previous one in the green, were reported by Yasuda and coworkers late last year, this one at 22% external quantum efficiency. Now, all of these numbers may seem quite impressive, and indeed they are, but one of the issues has to do with looking at efficiencies at practical luminances. So it's all fine to have very high maximum efficiencies, but what counts is an efficiency at a practical luminance in your display or in your lighting. And so if we look at 100 candelas per meter squared, we can see that the values now are quite a bit lower, and that's because the efficiency lower off in these devices is relatively strong. In other words, this is a problem that needs to be overcome in these devices. One of the reasons why there are, relatively speaking, so few multi-resonant TADF emitters is because computational methods on the whole predict the properties of these compounds rather poorly. And that's what's shown on the right, where we are trying to calculate or predict this key delta EST parameter. And no matter what type of density functional method we use, we systematically overestimate the actual value. It's only when going, excuse me, to couple cluster methods that we were able to accurately model these three compounds. And we published this now a couple of years ago in Nature Communications. We've since gone on to model 35 other multi-resonant TADF emitters, and you can see that across this entire set, couple cluster calculations do a far superior job in predicting the overall properties. And once we have a method to do this, we can now start to in silico design new multi-resonant TADF emitters, and that's what's shown here. These were all designed about 3-4 years ago now in our lab. The first one we call INDABNA1, and that's because this is an analog of a compound that had been previously reported in the literature, but where the nitrogen and boron atoms have been inverted. In other words, in the literature compound, the boron is in the middle, and where the two borons are, there were nitrogens. And then we went on to look at this compound, DICTA, and its mesatylated analog, a compound I showed you previously. This DICTA compound had been reported in the 1990s as a fluorophore, but when we calculated it, we predicted that it would be multi-resonant TADF. And so I had presented this work now a couple of years ago, and in the audience was a colleague friend of mine, Professor Sining Wang. And when I showed this to her, she said, my goodness, we've been synthesizing compounds of this type. Perhaps these two are multi-resonant TADF emitters, and in fact, they all are, and we collaborated on this work. But if I could really focus on these ketone-containing multi-resonant emitters, these two structures have a helical conformation with electrochemistry that is very well behaved. If we look to the solution state photophysics, they're nice blue emitters, not very emissive in solution. We'll get back to that in a second. One can see that when one exposes these compounds to air, the delayed emission, that is gets rapidly quenched if one compares the black to the red line on the right. And one can see that the emission is quite narrow, with a full width at half max of around 35 nanometers. Delta EST is still relatively small at 240 millielectron volts. One can see, and I've shown this data earlier, that the nature of the emissive excited state of these compounds is short-range charge transfer, and you can see that because of the small degree of positive Silvatochromism. One can observe directly the thermally activated delayed fluorescence by doing temperature-dependent time-resolved decay. And so what you're seeing here, we've now migrated to a 3.5 weight percent MCP film that at room temperature, one sees a prompt emission followed by a delayed emission. Those are the sort of two separate parts of the decay curve on the left. But no matter where we look, from 6 nanoseconds to 5.5 milliseconds, the emission is always coming from the same state. However, when we cool the sample down now to a very cold 5 Kelvin, all one sees is prompt emission and phosphorescence. And so after about 6 nanoseconds, there's no more of the emission in the blue, and instead what pops up is an emission or a phosphorescence at around 530 nanometers. Is present. So one can take that data and extract out delta EST values, and one gets values somewhere between 240 and 270 millielectron volts, depending on which compound we're talking about. And these values align very closely with those predicted by couple cluster calculations. Why have the mesotyl groups on these compounds? Well, this now comes into stark relief. One can see that without them, as one increases the concentration, there is an extra band that forms. This band is due to aggregate formation, and that is completely suppressed with the presence of these bulky mesotyl groups. Moreover, aggregation caused quenching is also largely suppressed, at least at doping concentrations up to 10%. And so this is one of the detracting features of multi-resonant TADF emitters, where without these types of bulky groups, these compounds really have to be used at very low doping to mitigate against this aggregation caused quenching. And here we demonstrate that we can get around it. If one looks at the devices and we focus maybe specifically at the mesetylated dicta compound, the compound on the right, one can see that the emission overall is, or the maximum external quantum efficiency overall is quite high, 21%. And more importantly, when we go to 100 nits, 100 candelas per meter squared, the efficiency stays reasonably high at around 15%. The only detracting feature for these devices is the undesired redshifting as a function of the substitution. Indeed, we're working on that now. We will go on to make a dimeric analog of dicta that we call didicta. This compound too is predicted to be multi-resonant TADF emitters, but because of now the pseudo-degenerate singlet and triplet states, we now have an increase in the density of states, and that's going to help us later on in terms of the efficiency of our RISC process. One can see that, like the compounds I showed previously, the emission is very narrow. Delta EST is about the same value. One can see the TADF property in place at room temperature. Doesn't matter where we look, the emission is always from the same state. However, at low temperature, and this is now in the film and DPPO as a host matrix, delta EST is 160 milli electron volts. Importantly, we can calculate an activation energy for this process, and one gets an activation energy of 40 milli electron volts. And the reason why that's smaller has to do with the fact that we have these now pseudo-degenerate states that aid in the RISC process. We can now make devices where we can go all the way up to 12 weight percent without much detracting features in terms of the maximum efficiency. That's around 19%. And at the time we published this early last year, this was only the second example of a green multi-resonant TADF emitter, and still one of the best performing ones out there. We next were interested in investigating the effect of substitution around this dicta core, and so we went about making these 7 compounds, and they can be classed into two separate families. There is a class of compounds that contain carbazole only that showed this characteristic short-range charge transfer, and then these other 4 compounds which have stronger donors in one form or another that have a quite unusual emission in the sense that at more polar solvents, we start to see the appearance of a standard donor acceptor charge transfer excited state. So we'll put those aside because their photophysical properties are more complicated. Instead, focus on the ones just with carbazole. And one can see that for each of these compounds, emission is very bright. And depending on the number of donors, one can tune the emission all the way from sky blue through to green and all the way into yellow. And this is one of really the first examples of a yellow multi-resonant TADF emitter. Delta EST values are smaller than the compounds I showed beforehand, yet they suffer from reasonably long delayed lifetimes. Because the emitters are so bright, we can now make devices with very high external quantum efficiencies, up of around 25%. This is amongst the highest efficiency devices that we can make in St. Andrews. The only detracting feature, again, is the severe efficiency roll-off, which isn't too bad at 100 candelas per meter squared, but when one goes to 1,000 candelas per meter squared, now efficiency is quite low. The final type of molecule I want to show you is something quite distinct from the compounds I showed beforehand, which is this boron nitrogen doped heptacene type structure. And I'm showing you a crystal structure right here. On gold surfaces, they happen to self-assemble into these herringbone structures of dimers that form. That's only true on the gold surface, and both in solution and in the film that I'll show later, they don't do this. This compound, despite the very large conjugation length, is actually predicted to be a near UV type emitter by our couple cluster calculations. And just to show you how important it is in terms of the regiochemistry of the doping atoms, if I switch out the boron and nitrogen and I invert their position, now I get something that's predicted to be quite a bit more redshifted. But if we focus on the compound on the left and we look at the photophysics, this is now in THF solution, one can see an emission maximum of 390 nanometers, a full width at half max that's very narrow at 31 nanometers, a delta EST that is pretty much bang on what we predicted beforehand at 310 millielectron volts. This is on the high end for something that is TADF. The photophysics is quite distinct in terms of what we see here. At early times, we see a prompt fluorescence, that is this emission over here. And then at intermediate times, we see the growing in of this particular band, which we attribute to an aggregate type formation. This then disappears. And at very long lifetimes, what we see is this phosphorescence occurring from the monomer type emission. The delayed emission is complex to model. At lower temperatures, all we see is an emission that decays as T to the -2, and this would suggest that despite the linear dependence on power dependency, that this is due to triplet annihilation. However, when one increases the temperature beyond 200 Kelvin, all the way past room temperature, now we see the delayed emission that is thermally activated. And so what is actually happening here are three separate processes. We have a prompt emission with a lifetime of 8.5 nanoseconds. We have a delayed fluorescence due to TADF that is extremely short at 450 nanoseconds. And then we have another delayed emission component due to triplet annihilation. And the triplet annihilation occurs because these compounds, even under very dilute conditions, have the propensity to aggregate. And one can see this with the appearance of this aggregated state. That's what's in green here. And we can remove this aggregated state simply by sonicating to recover the initial type of emission that's shown beforehand. With compounds that are so high in energy, it's very difficult to design an OLED with suitable host materials. And in our initial attempts, we've been able to make an OLED that turns on. However, as one can see, the efficiencies are extremely low at less than 1% in this device architecture. So what have I shown today? I've given examples of new multi-resonant TADF emitter design and shown you high performance deep blue to green OLEDs, particularly based on these triangulene type structures. I've shown that it's possible to tune the emission by judicious decoration of these multi-resonant emitters, going all the way in this presentation from near UV all the way to yellow. I've shown an example of a linear type structure, so we can move beyond these triangulene type structures to generate something that is ultra deep blue in process. Finally, the most important slide, and of course this image is rather dated now due to COVID, but I have a really dynamic group of students and postdocs that work with me. And all the work that I've shown has been the result of these four people. In the top left is David Hall, who's really, who's a finishing PhD student in my group, who's really pushed the computational modeling of these compounds and designed these and the original Dicta type compounds. Dr. Dianming Sun, that's the top right person, really piloted the Didicta work that I showed immediately following the Dicta work. Dr. Suresh Suresh, that's immediately underneath, is another fantastic postdoc in my group who really drove the alpha-3-BNOH, the heptacene structure that I showed in the end. And finally, Sen Wu, who's a fantastic starting PhD student in my group, has done all of these Dicta derivatives where there were different donor groups attached to them. I'm also thankful to these collaborators. This is multidisciplinary research. It requires collaboration to generate the high quality science that comes out of my group. And in particular, the groups of Ivor Samuel at St. Andrews, Johan Olivier at Namur, who's a computational chemist, and Anna Kohler at Bayreuth have been instrumental in bringing this work to fruition. And finally, these funding agencies who have subsidized or underwritten the work in my lab. And finally, thank you very much for your attention. I'd be happy to answer any questions.
Professor Coleman. This is Ajmal from Riken, Japan.
Yes, hi.
Yeah, hi. Very nice talk and very interesting. I'm working on 3.5 LED, UV LED here. So I saw your organic LED is very interesting. If you go to slide number 38.
Yeah, I'll reshare the presentation, so I'll do that.
Yeah.
Okay.
If you can go to slide number 38. Maybe not so pretty far. Yeah.
Yeah. This one?
No, the previous 37. Can you go? Yeah, more back.
Yeah,
Yes.
I'm coming. I'm going.
Yes.
Yeah.
This one. I see the dotted some photoluminescence curve or the peak around the UV region.
Yeah. So this is the absorption spectrum that's here.
Right.
Dash line.
Yeah.
Okay.
So it's based on your Neve organic material, or I mean, can you design the UV emission by organic material?
Well, this is in fact what we've done. I mean, I called it deep blue, but really, you know, at 390 nanometers, it's charitable to call it deep blue, right? It's a near UV emitting material. It is very difficult to generate UV emitting materials. So there are probably only, at least for this thermally activated late fluorescence type compounds, there's maybe only 4 examples out there in this energy regime.
But excuse me, Coleman.
Yes.
I believe this peak is not 390 actually. The dotted one is maybe 320 nanometer or something, or 330.
No, this is the absorption spectrum. What you're seeing is a dash.
I see.
Okay.
I see.
PL at room temperature is this red one. This is 390. Here,
right.
Where my cursor is.
Right. So, okay, just I need your future words about your OLED. So, is there any possibility to make a UV emission from OLED?
Probably not to 320 nanometers, right? At some point, or not at 320 nanometers with any degree of efficiency, right? So one needs to design a material if one thinks about what's required, right? One needs to design a material with an emissive excited state at that energy range. One needs the triplet state to also be at about that energy range to have the small delta EST. And one of the issues becomes, and this is why blue emitters that are based on organic compounds are so so unstable, is that you start to reach energies for the excited states that are of comparable energy to the bond dissociation energies of the compounds that you're looking at. And so what happens is you don't get emission from the states, you get bond scission that occurs. So I think I wouldn't be holding my breath to get anything much more UV than what we already have here.
Right. So how about any possibility of the energy band gap engineering by organic? Is there a new material possibility of the new material to have more wide band gap for UV side?
I think one could design something that's slightly bluer than what we have, but the question is, why would you? I mean, I guess there are certain telecommunications applications that you would.
No, okay, I understand. Because one of the very great application is for agriculture. I mean, you can grow plants under UV light, and you can produce a lot of antioxidant matters in the plant for So, and also for the COVID, like COVID-19 virus can be killed by 222 nanometer. So,
sure.
So it's a lot of application, but the 3,5 material, for example, Algan, if you're using, so it has the problem with p-type. So when we make a PN diode, so the number of electron is pretty enough, but the hole is a very big challenge for us. But if we can find some organic material, I mean, like in the perovskite people, in perovskite solar cell, people come up with the alternative, the silicon or some other. So I was just thinking that's like you reach to 390 nanometers of wavelength, but
if there's some possibly more deep UV or UV, it has a lot of industrial. I can give even 1 hour talk about the application, but I don't want to talk now. So it's very important.
I think you run into stability issues as one goes even more into the UV. So organic compounds can go way out into the near IR, and I think there's a lot of space that one can improve, but going to this side becomes even more difficult. And even if I could design a molecule that did it, that emitted, unfortunately, I would need a host material that had an even higher band gap in order to confine the excitons on the emitter material. It becomes nearly impossible. Already at this energy level, we're really, really limited in the number of hosts that we can use that have even larger band gap than this compound. It's incredibly challenging.
Yes, incredibly challenging, but not impossible, right?
Like I said, I wouldn't hold my breath. Impossibility is an absolute, so I also would never say impossible, but likely not to happen anytime soon.
Yeah, so it's very interesting for me. I know the professor you talk about, the Japanese professor. I know him here in Yokohama University. Yeah, and so they're working on more or less same area. But so I will keep in touch with you in future if we can dig out something together. Yeah.
Happy to chat. Absolutely happy to chat.
Yes. And thank you very much for your time and for nice talk, and especially for saving your time for Pakistan. And thank you.
Oh, my pleasure to come and speak to you all.
Yeah, thank you.
Are there any other questions?
Yes, Eli, I have a question.
Hi, Tariq.
Yes. So you showed that the multi-resonance TRF, they have a high efficiency in blue and green, but the efficiency in the red was a little bit lower than that one. So what is the limiting?
I'm not sure there's anything that's limiting. I think there's been only 2 papers out. So I don't conclude too much from 2 examples, right? That's really the case. I mean, between you and me, apart from the fact that there are only 2 examples, there's an energy gap law component that needs to be considered in terms of increased non-radiative decay in red emitting type compounds that needs to be overcome. But I'll put it to the fact that there's just too few number of examples to conclude anything for red.
Okay. Yeah. My another question is, so you showed that you can get the narrow emission. So you solve the problem of that broad emission, and you have a more color purity. So in terms of the stability of the devices, how stable these devices are?
So as I'm sure you probably know, we don't actively check for stability, but if I use efficiency roll-off as a surrogate for stability, what I can tell you is that we have not compounds that I showed here, but we do have other compounds where delta EST is quite a bit smaller, and that's led to devices that show, relatively speaking, lower efficiency roll-off. And so given that there's lower efficiency roll-off, I would expect the stability of those devices to be better, but we haven't actively tested that already. There are other ways to use these types of compounds, and that is in what's called a hyperfluorescence configuration, and there the stability of those types of devices for TADF is quite high.
Okay.
So long as you can cycle your triplet excitons off quickly and get them to radiatively decay, you'll be okay.
Yeah, I was thinking in that way. Thank you.
Are there any further questions that I can answer? Well, if not, thank you very much for the invitation, and thank you very much for allowing me to have a chance to present my group's work. And good luck with the rest of the conference.
Assalamu alaikum. May I start my talk? Hello. Hello.
Yes, madam, start करिए.
Can you see my slides?
Yes, madam, start.
Okay, thank you so much. I would just like first to thanks to the Multan Women University that they are organizing the international conference, specifically on material sciences. I'm not the part of the material sciences because, yes, in other words, I belong from the theoretical branch of the plasma physics, but might be it's a bit difficult for the understanding of this phenomena in the plasma. But anyway, they invite me for the talk, and today I'm here. I thank you for the speaker as well as, again, thanks for all the participants. And the title of my today talk is different type of nonlinear structures in high temperature gradient mode. One of the major problems of the controlled fusion is the particle and energy losses due to anomalous transport across the magnetic field. High temperature gradient instability are the dominant contributor to the turbulent ion energy losses in tokamak. The main contents of my today presentation is the motivation, the introduction, model equation, the linear analysis, nonlinear solitons and shocks, parametric analysis, and then finally we conclude the talk. We observe different type of nonlinear structure like the wake vortex turbulence, like the wing tip vortices, the turbulent flow, solitary ocean waves in different medium, either on the surface of the earth as well as in the astronomical objects. So why these things are important for us? Plasma is intrinsically, even we observe this type of structure on the surface of the sun as well. So plasma is intrinsically nonlinear, and the diversity of the wave in the system can give rise to structures such as vortices, solitons, and shocks, which plays an important role in transport phenomena. The study of these structures is also important in the exploration of space plasma regions, for instance, Earth auroral regions, solar atmosphere, and other astrophysical plasma. These structures have lifetime more than their own period of internal mutation and are important for heat, mass, and momentum transport. The solitons in space observed by the spacecraft named as the Samba, Tangu, Romba, and Sansa of the cluster mission on 30th March 2002 while crossing the Earth magnetopause. So why this mode is very important for us? The existence of the strong gradient at the boundaries of the warmer region may trigger drift instability, which acts as a damping mechanism to further increase of gradient in temperature. And tokamaks, one of the most important core drift instability is the ITG mode. ITG mode are considered as cause of the anomalous ion heat transport in high temperature core regions of tokamak plasma. Recently, the large helical device of the National Institute for Fusion Science succeeded in generation of the high ion temperature by means of the neutral beam injection. Observed ion temperature profiles are steeper than density profile. Thus, the ITG mode are expected to become unstable and drive the anomalous transport in helical system as well. So Tassu derived a nonlinear equation for inhomogeneous plasma having electron temperature gradients and pointed out the Shotland structure. Deacon et al. Discussed the electron temperature gradient are necessary for the drift solitons. So what is the mechanism of ITG mode in atomic plasma? The instability occurs due to the nature of the grade B drift. The grade B drift velocity of the particle, look over here, caused by the gradient in the magnetic field is proportional to the particle kinetic energy. The hotter particle drift further the colder particle. Hence, if the temperature gradient is aligned with the magnetic field, then the particle in the hotter region will drift further. If there is a perturbation in the temperature gradient, then the difference of the drift velocity will create the charge separation. And the charge separation creates an electric field. So this electric field creates E cross B drift, which increases the perturbation amplitude. Ion temperature gradient, ITG, is defined as a type of plasma turbulence produced and sustained by the ion temperature gradient. Mathematically, we can express the ITG mode like eta I is equal to ln by LT, where ln and LT are the densities and the temperature scale lengths. So this drift is usually called the eta I mode. This instability was first studied by the Ragatov and Sagadev in 1961 using the uniform density and non-uniform temperature. The eta I mode instability is caused by free energy stored in the equilibrium state. We assume that the ion electron ion plasma embedded in a uniform magnetic field along the z direction. And we further assume that the gradients in density as well as the temperatures are along the x-axis. We are neglecting the electron inertia and working on the ion time scale. So plasma species obey the Boltzmann distribution with the help of this equation. So the mode frequency is much smaller than the ion gyro frequency. These are our assumptions. We are familiar with the Navier-Stokes equation. The first one is the ion momentum equation, in which Ez is the Z component of the electric field, and we assume that it is purely electrostatic. Pi represent the ion pressure term, the gradient of the pressure term, and inside the pressure term, we have the density as well as the ion temperature, respectively. So the ion continuity equation can be expressed in this equation. Since we are interested in an ITG-driven mode, for this purpose, the ion temperature perturbation is attained by energy balance equation, which is expressed in this form. So this last term, Qi, is nothing, it is just a heat flux term. Under low frequency limit, when we assume that omega is very, very less than omega Ci, we yield this equation, which is the total drift velocity and of the plasma, and which is the combination of the drift velocities of the E cross B drift velocity, diamagnetic drift velocity, polarization drift velocity, as well as the velocity comes from the stress tensor. And the last term is the Z component of the ions along the Z direction. When we combining all these equations along with the neutrality condition, we get this type of dispersion relation, which is the third order dispersion relation for ITG mode and electron ion plasma in the presence of ion temperature and gradient mode. So this last term, this one, in which the eta I, which is totally dependent on the ion temperature, is the main cause to destabilize the plasma. So we can plot this dispersion relation to find out the growth rate. From these plots, now that we have the effect of ion temperature through the parameter tau on the real as well as the growth rate of the unstable ITG mode based on equation number 5. So in the first situation, look at this when we are changing the ion temperature from 0.1 to 0.3 TE, one can see that increasing the ion temperature make the phase velocity to decrease as depicted in this figure. and the corresponding effects of the unstable root of equation 5 is shown in figure B. It is clear that increasing the ion temperature in this case make the growth rate to escalate. So the effect of tau is more dominant in the short wavelength region, while the effect is not prominent in the dispersionless limit as evidences from this curve B. In the second figure, we have shown that the effect of eta I, which is totally dependent on the ion temperature, one can see that increasing the eta I, which is clear from these figures that eta is 1.5 to up to 3. So it's make the real root to decrease, while the imaginary root of this equation is increases. So one can see that the effect of eta I is dominant in the regime of larger cases on the growth rate or rate of instability for the ITG mode. We are interested in the nonlinear analysis. So we consider the ion temperature gradient mode in the dispersive environment, whose constituents are electrons and ions. We further assume a co-moving frame in which xi is equal to y plus alpha z minus 2t, where u is the velocity of the nonlinear waves and alpha is a small angle. So the continuity equation, by using equation number 1, we have this type of equation by introducing this new frame. In the presence of this new frame, the momentum equation takes this form, while the energy balance equation has this form. We are combining all these three equations. We will get this type of equation, and the general view of this equation is represented by equation number 10, in which A1 is represented by this equation, A2 is nothing, it's totally dependent on all these factors, and in A3, the eta I term is dominant. So this equation is a KdV-like equation which admits the following localized phase, the pulse solution, in which phi m represents the amplitude of the wave, and it is defined as 3u divided by A, and W represents the width of the soliton, which is totally dependent on 4b divided by u, with A is equal to A2 by A1 and B is equal to A3 by A1 are defined for convenience. For a valid physical solution for condition, B must be satisfied, that B should be greater than 0. So this equation number 14 represents the ITG mode driven solitons. We observe this type of structure in this mode for the first time. In the parametric analysis, we observe that from this figure, when we are changing the ion temperature, one can see from the first figure that increasing the ion temperature makes the soliton amplitude is going to be decreases, while the width of the structure is increases. So it's mean that the effect of the ion temperature contribute to both the non-linearity and the dispersive effect in the medium. In the second figure, when we are going to change the eta I, so both the amplitude of the nonlinear structure are going to be increases. So the eta I contribute in the nonlinearity effect of the system. If we are going to change the magnetic field strength, so we can see that increasing the magnetic field strength, the dispersive property of the system only, the width of the structure is going to be changing, while the amplitude of the soliton is remain constant with the variation in the strength of the magnetic field. If we consider the effect of the dissipation on the nonlinear wave with propagation, a shock wave solution can be generated from the Berger-like equation. So the dissipation is modeled by adding the neutral ion collision in the momentum equation. As a result of this collision, a drift velocity Vc will be generated with the generation of nu n. So nu n is the being in the collision frequency. Hence, this equation, the momentum equation, take this form where we define any parameter F4 which just depend on the Larmor radius as well as the Newton collision frequency. So this equation is similar to the KdV-Berger equation and which gives the shock-like solution in this form. So this equation 17 is clear that the shock wave profile is strictly depend on the sign and the magnitude of C by A. From the numerical analysis, we observe that the shock solution based on equation 17 will affect of ion temperature to the ratio of the gradient scale length eta I in this figure. One can see that increase the ion temperature make the shock wave amplitude going to be decreases, while increasing the eta I make the shock wave profile to flourish, as evidences from this figure. So the effect of the magnetic field on the shock profile is shown in this figure, which show that the amplitude of the soliton is going to be decreases and the width retained its initial position. It is noticeable that the shock profile reveals the effect of temperature and eta I, but in the case of magnetic field strength variation, the shock profile shifts, but the steepening remains the same. So finally, we conclude that the IITG-driven solution and shocks is studied for the first time. The influence of different parameters of the stability is studied in the linear regime. So the effect of these parameters on solitons and shock profile is determined. The eta I effect is observed, and it is found that it significantly changes soliton structure and shock profile. These observations may have relevance to both laboratory as well as for the space plasma. Thanks for your time. If you have any type of question, I'll be waiting for a question. Have you any question, please? Any question from the audience? If no, then I say just thanks to all. Thanks for your time. May I leave?
Hello.
Oh,
Hello. Assalamu alaikum.
सलाम आवाज आ रही है
आवाज आ रही है सिकंदर
जी जी
ओके
जी जी मेरे पास नेट स्लो है इस वजह से मैं अपना जी जी मैंने आपको
ओके सिकंदर मैं आपको इंट्रोड्यूस करवा रहा हूँ फिर उसके बाद आप टॉक स्टार्ट कर ले ठीक है
ओके ओके
okay good afternoon and welcome all of you now the last session of this conference now the invited speaker are Dr. Sikandar Azam, Assistant Professor, Rifa International University, Islamabad. He published more than 100 papers, round about 136 papers, and impact factor 369. And he did his PhD from Czech Republic and work on computational physics. Okay, Sikandar Azam, please, you can start now.
okay thank you so much for the nice introduction so this is me Dr. Sikandar Azam is being introduced by Dr. Parag Zaman. So today I'm going to give a talk on the effect of manganese doping on the electronic and optical properties of the cesium zirconium fluoride using the ab initio study. So these are the outline of my presentation in which I will talk about that why I choose this class of material, and then I will talk about the theoretical approach that I have been used for calculating the different properties, and then I will discuss the result about the electronic structure, optical properties, and then finally I will conclude my results. So as we know that energy is the basic need of life for every human on the earth. So man is in search of the sustainable energy sources on a daily basis. So this energy may be in the form of light, heat, and electricity. With the development of new sources of energy, it is very important to reduce the energy losses during the conversion of energy from one form to another. So in this regard, devices that convert energy to light energy being developed continuously with the passage of time. That is mean the burning of wood, lamp, electric bulb, a fluorescent tube, and LED bulb like this. So the basic principle for Pladnic device is its light energy conversion efficiency. So keeping all these as of today, there is not a specific method that could predict the exact luminous properties of the phosphorus material. So these days, most of the researchers they rely on the quantum chemical ab initio method that shows a very efficient and mean they are very efficient these days since mean from a decade the people are working on this. So the main idea behind my work was that mostly the people who are working on the light emitting diode material. So the purpose is to replace the energy wasting traditional light sources by means of the energy efficient means by the LED lamps. So it's a great effort towards the electrical energy consumption through the world. It has been come to know that in coming 2030 or above, there will be a maximum demand of the energy, mean around 56% more energy will be required for the current to the current world. So that's why most of the researchers have converted their ideas toward the energy towards the electrical energy. So the first step that has been put forward by some researchers in 2000, and they work on this material that is mean they dope calcium, replace calcium, strontium, barium, silicon nitrate by doping the europium, and they got some good result that led to a commercial application in the passports converted light emitting diodes.
Sorry for Sikandar.
GG.
Sorry for interference. You are still on first slide.
I don't know. I have changed 2-3 of my slides. I don't know what's the problem.
But we see only the first slide. Please go on slide mode, I think. Then it's okay. You go to on slide mode.
It's work now?
No.
Okay.
Okay. Now
It's work
outlines.
now?
Yes. Please you go on
Okay.
slide mode.
Okay.
Slide mode. Maybe then it's working.
Okay. I don't understand what do you mean from slide modes. I'm
Here is this.
You mean like this?
Slideshow.
Excuse me, share the
Okay.
full screen. If you excuse me, if you hear me, shall I interrupt? You go here. That
Yeah,
click
yeah,
that.
yeah.
Yes, yes.
Okay, yes. I
Yeah.
already before it was like this, but Dr. Falazaman told me that the slide you are still on the first slide, but I was in the fourth slide. Now now it works.
No, not yet.
Slide you are seeing.
Dr. Sharafat Ali, it's working or not?
Not working for me. Well,
Yes.
the best will
Same
be,
for me.
yeah, you stop sharing and start resharing, so it might work.
It's okay now.
Yes, I think okay.
Hello.
Okay,
Okay.
let's go. Okay.
Okay. So, mean the work on the passports light, mean the on the light emitting diodes. For the first step, it has been studied in the 2000 by doping the europium, and the result which they obtained that has been commercialized, and their application were in the passports converted light emitting diodes. And that results a very numerous effort to develop a new high performance passports. So keeping all these things in mind, I have also focused on the light emitting diode materials, but instead of this material that has been it is very highlighted material in the light emitting diode material. That's why I mention it here. So I use some different type of material that is as mentioned before. So before to go deeply in that material, let me introduce the methodology that I have been used for calculating different properties for this material. So we want to predict the properties for this material, but the way how to do the quantum mechanical calculation that are based on the mini body problem. We can do this generally by quantum method, and secondly we can do this by Ab initio way. So in order to go further, it's very complicated to solve this problem. Using this mini body problem, it's very complicated because we have this Hamiltonian, and this Hamiltonian is summation of all possible interaction between electron and nuclei, where the first term shows the kinetic energy of the electron, the second term shows the kinetic energy of nuclei, the Coulombic interaction between electron and electron, the Coulombic electron interaction between the electron and nuclei, and the Coulombic interaction between the electron and nuclei. So, for this, in order to solve this mini body problem, we need some approximation in order to solve this. So the first approximation that has been developed is known as the Born-Oppenheimer approximation. So as we know that the mass of the nuclei is larger than the mass of the electron. So the response of the electron is much faster than the response of the nuclei. So that's why they kept constant the nuclei and only kept the electron. But this approximation has been failed due to the decoupling. So we have many body problem, and there are many systems that has thousands of atoms. So and almost there are 10 raised power 23 electrons per centimeter. So there are two ways to deal with this, with a huge number of systems, with a complex system. So the main work that goes behind is the density function theory, because in the density function theory we can deal with a very big system, and that goes towards the Hohenberg-Cohen theorem, in which they studied that the total energy in the presence of the external potential is a function of this. So they gave the statement, but it was not the final one, because they get something about which they don't know that what to put for this functional. So again the problem. So later on, after 2 years, the Cohen and Sham, they gave the exact statement, and they decomposed this functional into the kinetic energy of the electron, the Coulombic attraction between the electron and electron, we can say that, and they also added something that is known as the exchange correlation energy. So now the problem is almost 90% has been solved, but the problem still exists. That was that what to use for this, that how to solve this problem, the exchange correlation energy. So for this, there are different approximation we can use in order to solve this problem. And the basic ones are the LDA, local density approximation, and the generalized gradient approximation. So now we have the tool that allow us to calculate the properties, different properties for different materials. But the problem still remains there, that how to use the approximation and which approximation will be better for which material. So a good scientist, he could know about the nature of the material, that which approximation I can use. So for the accuracy, someone has to use a specific functional for the specific material or for the specific properties. As for the metals, the LDA, the local density approximation, was good. But for the semiconductor, the generalized gradient approximation, it was good. There are transition metal. For that, we use the Hubbard parameter, mean the dft plus u. And nowadays, these days, the researchers are working to get some good results. So they are working on some different approximations. So if we use the generalized gradient approximation for the semiconductors or for the insulator, so almost the results are underestimated or overestimated with the experimental results, and they almost goes around 30% to 20% or something like that. But these days, a new approximation has been developed that is known as the modified Biggie-Johnson approximation, and that gives very close result with the experimental, and they're almost plus minus 2% of overestimation or underestimation with the experimental results. So we have the tools, that is the density functional theory. Now we use some specific methodology that should be used in order to get some specific method to deal with the material. So this is the unit cell. For this, what we do, we decompose this unit cell into two regions. The first region is
Sorry, Sikandar. No one see your slide. Just see only the third slide. You are still in third slide, and no one see.
I don't know what's the reason.
सिकंदर
जी
आप इस तरह करें, ये कमेंट्स और इसके साथ ये स्लाइड शो नहीं है जो प्लस माइनस माइनस के साथ, ये आप ये वाला जरा उसको क्लिक करें।
सबर के कौन सा वाला प्लस माइनस?
एक मिनट, आप दोबारा शेयर करें स्क्रीन शेयर।
या मैं कहाँ पे आप इसकी बात कर रहे हैं वाला?
एक मिनट, आप स्क्रीन शेयर करें।
ओके
अच्छा, ये जो कमेंट्स ये नीचे है ना, तो ये प्लस और माइनस ये जो स्क्रीन का जोड़ा यहाँ पे ये इसके साथ जो है, इसके साथ ये लेफ्ट साइड पे ये वाला आप क्लिक करें।
ये तो मतलब वो तो फुल हो जाएगा ना?
हाँ,
ये
तो
मैं
ठीक है ना,
लेकिन फिर भी आप लोग कहते हैं कि वहाँ पे कुछ प्रॉब्लम आ जाता है।
हमें शो नहीं हो रहा,
अभी भी शो नहीं हो रहा,
स्लाइड शो नहीं हो रहा, मतलब शो हो रहा है लेकिन वो आप जरा नेक्स्ट करें। नेक्स्ट
मैं करता हूँ, ये वाला ठीक है। नहीं हो रहा,
मेरे साथ तो नहीं हो रहा ये। बाकी डॉक्टर शराफत, अब्दुल गफार,
अब यू कर लेना, पूरा कंप्यूटर का स्क्रीन शेयर करो, सिर्फ ये प्रेजेंटेशन नहीं। तो
हाँ, ये बात सही है। हाँ
बिल्कुल, ये फर्स्ट टाइम है कि इस तरह मेरे साथ होता है। I don't know what's the reason.
It happened sometime. It's nothing first time for us at least.
Let me.
Dr. Sharafat, how are you, sir?
So far, so good.
Your talk is tomorrow? From Sweden. He is from Pakistan.
अब ठीक है?
Now press your presentation.
It works?
We don't see the presentation.
I am also not
actually.
पर एग्जामान कोई और है जो मतलब अभी दे दे, मैं देखता हूँ क्या इशू है मेरे साथ।
अब यू एक काम कर ले, अपना प्रेजेंटेशन पखर को मेल कर ले और वो स्लाइड चेंज करता रहेगा। That can be another.
ठीक है, मैं मेल करता हूँ। ओके
भाई,
थैंक यू, मैं करता हूँ। ओके
या मुझे व्हाट्सएप कर दे फिर।
ठीक है अस्सलाम वालेकुम। वालेकुम सलाम। पता नहीं कह रहे कि मैं स्लाइड चेंज करता हूँ, कहते हैं कि स्लाइड चेंज नहीं हो रहा। मैं पहले जमान को मैंने की है, चलो मैं आपको भी कर देता हूँ। ठीक है, व्हाट्सएप पे मैं कर देता हूँ आपको। ठीक है, ओके ओके।
Hello, Sikandar. Hello. Hello. Hello.
Yes, Fakhar, we hear you.
Okay, now you see my
Hello?
screen, sir.
Yes, I see it, and I think it should change now. You just change it if it's possible to see the other slide.
Okay.
Yeah,
Okay,
now
now it's
it's
working.
changing. I think we are losing the time, so just start it.
Okay.
So
कौन से slide पे जाओ?
Next. Okay. So a bit later, previous one.
This one.
Okay. So as we talked about the tool that we have the tool, but now we need the methodology. So for that, what we are doing, we just decompose this universal into two regions: the atomic sphere region and the interstitial region. So why we do this? Because here we can see that near the nuclei we have the rapid oscillation, while the region between the region where it is very smooth plane waves, where we can also say a Fourier expansion can be a good set for this smooth part. But here, that is very close to the atom, we have strong oscillation. But with the Fourier series, we would never be able to describe this. So what we do, therefore, we do add something that is in the description in term of the atmospheric, in the term of the atomic partial waves. So we can solve this problem, mean that are the numerical solution of the radial Schrodinger equation in the spherical potential for particular energy. So we can now the problem is how to solve it. So nowadays it's not a big problem because of the big heavy computational systems, but the main problem is of this energy, that how to calculate this energy. So please go next. So we have now the tools, we have now the method. They allow us to calculate the properties, different properties for any investigated material, for any properties. So the one that I have choose, the material that I have choose is this material, in which I have doped the manganese in this by making a supercell for the cesium material. So I dope manganese 2.5%, 5.8%, and 8.3%. So these are my doping percentage, and these are the optimized structures. Firstly, I optimize the structure by using, please go to the next slide. So these are optimized structure, and I use the Win2K code and use the pole potential linear augmented plane wave method. Firstly, relax the geometry by using the generalized gradient approximation. The results are very close with the experimental result. So as we have the cesium in this material, but I didn't use the spin orbit coupling. So the calculation for this spin orbit coupling are already in progress. So here I have calculated the two different properties, that is the electronic structure and the optical properties, by using the modified Biggie-Johnson approximations. So please go next. So these are our calculated band structure. This is for the favor form, mean for the parental compound. That shows a very heavy band gap, that is 7.3 electron volt, and its application lies in the ultraviolet regions. So for that, in order to get the to play with the band gap or to do some engineering with the band gap. So what we did, what I did, I just doped the manganese in this material that reduced the band gap of the material. Please go next. So this is the density of states for the parental material, and in order, the main reason behind calculating the density of state, because if we look to the band structure, there we don't know about the character of the band, that what the characters it shows, that mean at which energy point, which orbital we have. So for that purpose we have calculated the density of state, the total density of state, and the partial density of state. The total density of state, we can know about the concentrations, that at which energy point we have greater concentration or which have greater density. By calculating the partial density of state, even we can know about that at which energy point we have the major contribution comes from which orbital. So here we can see that near the Fermi level, the major contribution it come from the fluorine, while in the lower valence band it comes from the manganese D state, while the higher conduction band it comes from the cesium D states. Please next slide. And these are the band structure for the dope material, and that is here we only show for the 2.5% manganese dope. So as I talked about before, that the band gap for the parental material, that is 7.3 electron volts, mean its application lies in the ultraviolet region. But as I told, the manganese 2.5%, the band gap suddenly reduced, and it comes to around 3.6 electron volt, and for the 5.6 it comes around 3.6 electron volt. And the only reason that is because at 2.8% we have the band gap for the up state and the down state. For the up state is this one, for the down state is this one. But as I drop 5.6% manganese, so the band gap a bit increased. But again, after dropping 8 point something manganese percentage of the manganese, the band gap again reduced, and it comes to 3.4 electron volt and 4.4 electron volt. So means that as we have the main the main aim behind my work is to get the absorption in the visible region. So mean that if we could play with the percentage of the manganese or with the position of the manganese, so maybe we can get a good result, or the result that we are required to get the minimum absorption, the maximum absorption in the visible region. So we can see here that as the region mean one from 0 to 1.7, we have the infrared region. 1.7 to 3.1 electron volt, we have the visible region. So we need such a material that shows the major absorption in this region. Unfortunately, here again we have the application, it lies in the ultraviolet region, but it can give us the idea that by increasing the doping percentage of the manganese or just replacing the manganese position, maybe we can get the required results. Please go ahead. And this is the density of states for the 2.5% doping manganese. So the main reason behind calculating the density of state, because I'm interested in the optical properties, and from this graph, mean from the partial density of state, I can get know about the transition that take place from the valence band to the conduction band. So I can get know somehow from this picture that the first peak that come from which transmit from which orbital to which orbital the transition occurs. And so we can get know something from here. So, and it also gives the partial density of state also. It refers to a number of possible states at a certain energy. So here we can see that the major contribution at the valence band, at the maximum valence band, is due to due to this state, and this state is the manganese S state that is near to the Fermi level, and also here the D state is also around somehow here in the near the valence band. So the major contribution of the manganese, it comes at the upper valence band, and also at the in the lower valence band, and also at the upper maximum in the upper conduction bands. Next slide. So as my interest was to calculate the optical properties of this material, so the compound that I have chosen, it shows the triclinic symmetry, and there are many non-zero components. So here I will focus on those major components that correspond to the electric field perpendicular and parallel to the C-axis. And also for the transition, in order to identify the transition that are responsible for the spectral structure of the optical dielectric function, I will use my calculated density of state and band structure. Next slide, please. So this is our calculated dielectric functions, mean the real part and the imaginary part. So the real part, it shows the optical dielectric function of the manganese S state, and also
Hello.
Hello. Okay, I think Sikandar have problem with electricity and internet, so we can stop here. And who is the next speaker? Hello. Hello. Are you hear me?
Fakhar, accordingly, the schedule, I think it was the last presentation for today.
Okay, then we can wind up today.
Yes, it's look like that.
Yes. Okay, sir. Okay, sir. Tomorrow is your talk.
Yeah.
Hmm. And what about your talk according?
Wow. It will be more like about the glasses and the thin films. And the focus will be a strong glasses. And I will also slightly talk about what we are doing, like different project. We are working with bioactive glasses, with white LED and so on. So it will be mostly focusing on my research, basically.
Okay, sir, are you present at 9 a.m.? Are you listen the talk of
9
Chakrapam?
a.m. Swedish time. I think the Pakistan time is 12 to 12:30. Accordingly, the new schedule, which I got it very recently.
So today, are you listen the talk of Dr. Chakrapam? He is also talk on glass technology.
Doctor, what you will say it again?
Dr. Chakrapam, the first speaker of today.
I think I missed it, the first speaker, because it's very early in the morning in Sweden, 6 o'clock. So I'm not a morning guy, and anyhow, I don't see the title, so it was not possible who is talking. So that was the reason. So we are 3 hours backward from say from Pakistan. So let's. Do you have any other question, Fahar? Falak,
No,
sorry.
sir. No, sir.
Okay,
Falak.
then
No,
I
sir.
think see you tomorrow then.
Tomorrow.
And I think
Yes,
I will have the presentation at 12 o'clock local time. Okay, bye.
Yes, and I have presentation on.
I think you
I have
have presentation at
10:30 to
10:30.
11. If
Yes,
you have time, then please join me at that time.
I will try my best actually. 10:30 will be like 7:30.
Very early.
7:30 is possible, but 6 is a bit too early, so 7:30 wouldn't be an issue. So that I can do it.
Okay, see you tomorrow, sir.
I will try my best.
Okay,
Okay.
thank you.
Yeah, bye.
Okay, sir. Thank you, sir. Bye. Bye. Sir.
Assalamu alaikum. Assalamu alaikum. Hello.
हेलो
वालेकुम अस्सलाम सर आ रही है
ठीक है चले जाओ कोई इशू नहीं है ठीक, ओ।
Okay, now Dr. Asghar Ali, should I start, please? Hello.
Hello.
Can I start now? Hello.
Sir, you can start, but there is a lot of noise coming from your side. Maybe you can tune it.
Okay, please wait a moment. I should. Hello, can you listen to me now?
Yes,
Please?
it's fine now, sir. Thank you.
Thank you very much, Professor Rani, especially for inviting me for this talk. The title of my presentation is Synthesis of Nanostructures and their Light Absorption Application. And first of all, I want to introduce my institute, my university. I'm working as assistant professor at the Department of Physics, Khaja Farid University of Engineering and Information Technology. This is about more than 500 kilometers away from the Lahore. And I have been working in CINITAC, that is an institute of Chinese Academy of Sciences. Outlines of my topic is, first of all, I will introduce about the solar absorber, and then background and advancements in solar absorbers. I will go through the solar selective absorbers and broadband light absorbers. First of all, I want to say that most part of the energy consumption is originating from the buildings. What we are looking for, everyone is looking for the renewable energy that is most abundant, and also it is green, free of cost, and it is excessive. Most of the researchers are working on photovoltaic devices to harvest the solar light. But this part, that is a photothermal, most of the scientists are ignoring. I have focused on photothermal processes, especially for water and space heating. Photothermal process can be used in different industries, like we can produce thermal electricity. We can have technology for solar cooking, industrial processing heat, and many other applications. I have divided my talk in two parts. First is solar selective absorbers. And in solar selective absorber, we can use these absorbers. We are using the solar selective absorbers in concentrated solar power system. We are using this for heating purposes. And but in the market, what is the problem in solar in heating systems? In different heating systems, what we do in the solar geyser, for example, we coat our material on any type of pipe or on any type of vessel, and if the light shines over that vessel or that pipe, the water that is circulating inside into the pipes can be heated. But for most of the applications, we need that this coating should be stable at a higher temperature. For example, it should be stable at more than 300 or 200 degrees centigrade. What happened to this type of absorbers? There can be thermal expansion of metallic substrate if we are using metallic substrate. If you see right bottom, here is some problems that the solar industry, that the solar geyser industry is facing. First, when the temperature is high, then what happens? The copper substrate, mostly we use alloys of copper, so it diffuses into the absorber layer. The second problem is that interlayer, there can be interlayer diffusion or oxygen diffusion, due to which the efficiency of absorption efficiency is deteriorated. The third problem is that adhesion of the coating is poor with the kind of substrate. So in this study, we have designed a very simple solar tandem absorber that is based on titanium aluminum nitride, and then we coated SiO2 coating over that over the absorber layer. SiO2 coating is working as an anti-reflection coating. It showed very good stability and good adhesion with the substrate. It is a very simple structure, and it shows very low emittance. We have used this magnetron sputtering system to develop such kind of photonic structures where the light can be manipulated. This the first image which we see from the tandem absorber. The surface of the tandem absorber was porous. Most part of the incident light could be absorbed in such type of porous surface, and also we did cross-sectional SEM. I wanted to see its growth structure. If we see that its growth is columnar. Means there are columns. Once the light is shining on such kind of structure, the light can be manipulated into the structures, and finally the light can be absorbed. This is the reflectance spectrum. This is a pure copper the reflection spectrum from the pure copper substrate, and after depositing the TiAln absorber layer, the red color shows the reflection, which is very much minimized. It means that the falling light has been absorbed in the absorber layer. After depositing SiO2 anti-reflection coating, we could absorb the light, the incident light, completely in a specific region. To test the absorptivity, mostly we use alpha. This is absorptivity, and we also find the emittance. From this kind of structure, we have found the maximum absorption of 92%, and its emissivity was about 6%. The emissivity was tested at 70 degrees centigrade. Third, the problem we are targeting was its stability. To test the stability, we have tested our coatings, our device, tandem absorber at different temperatures in air. We have tested the samples at 350 degrees centigrade for 2 hours. Then put the same sample for 4 hours, and for 450 degrees centigrade till 550 degrees centigrade for 4 hours. We assume that if the coating is stable at 550 degrees centigrade in the air for 4 hours, it can be stable for longer period of time. To test the stability of the coating for longer time, a performance criterion has been developed. If the value of this performance criterion is less than 0.5, it is considered that the developed coating is stable. So from this result, we found that the PC performance criterion, the value of performance criterion was less than 0.5. It means that our coating was stable in air at 550 degrees centigrade. The same thermal stability was tested by the XPS. How we did this? to test the thermal stability, we put the sample. In fact, we asked the sample from the surface toward the bottom, and at the same time we were testing its elemental composition. From these results, and also from the Raman spectra, it is evident that the produced coatings were stable at high temperature. This is a small conclusion of this part of my work. A simple bilate titanium aluminum nitride based tandem absorber was designed, and we had achieved absorptions to emittance ratio 92% absorption, and its emittance was very low, that is about 6%. It showed very good stability at higher temperature of 550 degrees centigrade. Here, in this kind of structure, we found that titanium aluminum nitride layer was acting as a barrier layer as well as it was acting as an absorber layer. So the second part of my work is absorption of light in the photonic structure for wide band. Here in this work, we have achieved absorption up to 95% from 200 nanometer wavelength to 2500 nanometer. What kind of applications we have for such kind of broadband absorbers? The broadband absorbers are used in STPV system. This can be used for solar light absorption. Even we can use in photovoltaic devices. These kind of structures, these kind of materials can be used for the thermal regulation. Also, we can use such kind of black absorbers for the stray light reduction purpose. How we can achieve such kind of broadband absorption in a theoretical study that was published in Nature Material in 2014. They showed that if we are able to develop a conical structure having columns, then the incident light could be manipulated totally into such kind of structure. In literature, the different techniques have been used to develop such kind of structures. For example, lithography, laser pulsing, electrochemical etching, masking, etc. But most of these techniques are very expensive. But at the structure produced, especially by the lithography or laser pulsing or electrochemical etching, these are not stable in adverse conditions. So what we should do? We should find a very simple process. We should find a simple process. In this work, we had used magnetron sputtering system as I had showed you in the previous slide. Our fabrication process was very simple, and the main problem which is facing our industry is the stability of the coating. To test the stability of the coating of such kind of structures, we put our samples under the UV illumination for longer time, and after we had tested the samples under high humidity, I gave a thermal shock to the coating by putting the samples in preheated oven, and then put the sample out and put into the liquid nitrogen to give a severe thermal shock. Further, we have tested our samples at the elevated temperature, and also we have tested the corrosion resistance. This is there is a schematic diagram of the magnetron sputtering system we have used. Here, I should mention that in our magnetron sputtering system, there was we can use 4 different targets. we can use 4 different target materials. But I had used 3 targets, 2 of titanium and 1 of the aluminium, where we have been using argon as a protein gas and nitrogen as a reactive gas. In this case, the B figure shows the very beautiful columnar structures, and the C figure shows the scanning electron micrograph from the surface. So here, from B and C, it can be showed that we have been successful in developing such kind of nanophotonic structure where we can manipulate the light completely. This is a AFM image, and this is also AFM image. The more important thing is that this. We can deposit such kind of black coating, which is we can say that this is like black body coating. We have developed up to 5 centimeter, but in our system we have the capacity to develop the big sample like 20 centimeter as well. More importantly, this kind of coating can be deposited on flexible substrates. If we bend the sample, we found that the coating we couldn't find any kind of cracks. So it also shows its mechanical strength. This is the TEM image, which is further proof that the structure was columnar. This is a top of the columns. This is trunk of the columns, which shows that the coating is very dense. This shows the smooth, the very dense root of the columns. Next, this is a smart result that the developed coating was a polycrystalline. Its base plane profile and dense columnar structure, and the preferential growth orientation was along the 1-1 plane. Next, come to the UV visible spectrophotometer results, and here we see that this is a absorption versus wavelength, and we found that the first line is the absorption from the copper substrate, and then after depositing TiAlN coating over the copper substrate, so we found that the absorption is much higher, like it is about 86%. And after this is before depositing the any kind of anti-reflection coating. And from the emission spectrum, it is found that its point is near to the black body absorber. This is a schematic diagram representing the phenomena of absorption. So we have optimized different deposition parameters like nitrogen flux, sputtering powers of titanium targets, sputtering rate and thickness, and these are the results. I think maybe I don't know how much time I have, but we found that this method of deposition is a viable. So we have a big space for depositing the black body absorber coating. And then the important thing is its stability. We, as I mentioned, that we put exposed our samples in the UV light, under UV light, and also we put the samples under high humidity, about 85%, and then we give the thermal shock. These are the very severe conditions under which our samples showed a very good stability. So the first result is XRD, which definitely it is showing that there is some type of compression in the structure. but that is also evident from the SEM images. This is the Raman spectroscopy, and this is a very important result is that the absorption after putting the sample under UV light, after putting the samples under humidity, and also after giving a severe thermal shock, the coating structure was almost stable. So it is very clear from the SEM images, and it's very much clear from the AFM images. The second phase of testing the samples is testing samples at under high temperature, like 600 degrees centigrade in air. So we found that from the absorption results, we found that the absorption property was even stable after testing the samples for a 600 degrees centigrade for longer time. So again, we have tested its stability by using the XPS depth profile. Again, I should mention that we use the same method of etching the sample from the surface over the substrate, and we found that there is no interlace diffusion. Also, the copper substrate, we couldn't find any percentage of copper or silicon substrate into the absorber layer. So after the deposition, I also found that I wanted to know if there is only some reflection from where it is reflecting. I found that most part of the reflection was from the surface of the coating. So what I did to overcome this kind of reflection, I deposited two different kinds of anti-reflection coating. One was a mixture of TiO2 and SiO2, and I got the same result. Then I prepared another sample with an anti-reflection coating of TiAl-ON. So we found that most part of the light can be absorbed. I should say that all the instant light could be absorbed in such kind of structure. This is a small conclusion that stable ultra wideband light absorbers were prepared by a simple method. This unique approach to produce large area nanophotonic structures is free of any sophisticated patterning approach, substrate independent, and the process is viable and scalable. I gave the name of this kind of structure as Watton vertically aligned titanium aluminum nitride coating. These are black super absorbers. These are robustly stable in adverse environments. We found the broadband absorption of about 89% from the single TiAln layer, and 95% absorption after depositing the anti-reflecting coating. So this work was published in JMCC, and we have patented this this method. These are some my achievements. Thank you very much. This is my group where I have been working. Thank you very much. This over. Hello?
ठीक है आ